Hello, hi, namaskar everyone. My name is Dipendra and I welcome you all in this one short video of the chapter Limits, Continuity and Differentiability. Last year JEE Mains has asked 23 questions approximately from this chapter. I hope you're realizing that this chapter is considered to be a great chapter in terms of return on investment. The learnings, the concepts which we'll be discussing in this one shot are really simple and understandable, and you can master them with some simple efforts. And with that, you must realize that it covers a great chunk from your examinations perspective. The marks you're going to get will be huge in terms of investment which is needed to be done, which is required to be studied from this particular chapter. And we'll cover everything from this chapter, whether you talk about concepts, learnings, short techniques, formulae, and we'll consolidate all of this with a lot of previous year's questions. This one short video which is provided to you at absolutely free of cost. And in this one short video, along with this one short video, we are also going to give you the handwritten notes for your practice, for your revision, and the DPPs for your practice in the real-time environment. You can avail all of this by clicking on the link given in the description. It will redirect you to our PW app, from where millions of students are preparing for different competitive exams at affordable prices. So without any delay, let's see what we'll be discussing in this particular chapter. This unit is majorly divided into three parts: limits, continuity and differentiability. So first of all, the major chunk is limit, because even continuity and differentiability also use the same concept of limits only. But yes, few more things are introduced here which we'll discuss there, but majorly this entire unit revolves around the concept of limits, which we'll study in the first part. We'll understand what is the concept of limit, how do you find it, we'll understand different evaluation techniques and some different methods. And once you learn how to evaluate the concept of limits, once you understand how do you deal with concepts of limits, then we'll move towards the concepts of continuity and differentiability, that how do you ensure a function's continuity and differentiability with the help of the concept of limits. So this is all we'll be discussing majorly. All the three chunks are equally important. Questions are framed from the concepts of limits as well. Questions are asked based on continuity as well, and questions are based on differentiability as well. Major part is that if you understand these two concepts, everything here is going to use the concept in its core of limits only. So remember, understanding of limits is more crucial, or most crucial here. Let's get started. First of all, let's explore what do we understand or interpret by concept of limits. So if I could simply describe the concept of limits, first of all, let's take a graph, let's take a function. Let's say here we have a graph. I hope it's properly visible to you all. Now, if you look at this particular graph, here we have a function and we have drawn its graph like this. So let's say there is a point A on the x-axis. There is a point A on the x-axis. And what we notice is that on this point A, if I start approaching this point A from left-hand side on the x-axis, and if I start noticing the graph of the function, then I may notice that this function is approaching a certain value which we are calling, let's say, L. Similarly, if I approach this A from the right hand side, then also the graph approaches a certain value. Let's call it the same value L. So I hope most of you must be realizing that what I did was that I am not finding the value of this function at A. That is different. I am not saying that you need to find f of A. No, if this function is f of x, limit at x when approaches A is not equal to the value of the function A. This is something which you need to study. When you talk about the limit, so limit is written as LIM, limit. I usually write it as limit LT. X approaches A. So it first of all does not mean the value of the function at A of f of x. So what does it mean? It means that I am approaching A from left hand side on the x-axis. Then I'm seeing the graph, I'm seeing the pattern, that from to where is it leading me if I'm approaching A from the left hand side. That is called the left hand limit. And then I approach A from the right hand side, from its right neighborhood. And then I see its pattern, its trend, that where is it leading me. And what I can see is that whether I approach A from the left hand side or I approach A from the right hand side, the graph is leading me to a point which is considered to be L on the y-axis, which is considered to be equivalent to a value L on the y-axis. So when I approach this graph from the left neighborhood of A, when I approach this graph from the right neighborhood of A, I got the same value, the left hand limit and the right hand limit. Usually we write the left hand limit as limit x approaching A from left hand side, And we write the right hand limit as x approaching a from the right hand side. So a negative, a minus does not mean minus a, it means I'm approaching a from its left hand side. A plus means I'm approaching a from its right hand side. And what I saw or what I observed was that whether you approached a from left hand side or right hand side, fx was approaching L from left hand side and right hand side. So its left hand limit was also L, its right hand limit was also L. And if its left and right hand limit both are L, then we say that the limit of this function at A is equal to L. Now, of course, the chances are higher that the value of the function at A could also be L. Let's say the chances are higher that the value of the function at A could also be L, but it is not necessarily true always. But what you need to understand here is that if I am noticing that the function is approaching a value L when x approaches A from left and right hand side to from its neighborhood, then we say that limit x approaches A, f of x is L. Please understand, it does not mean that I am asking you the value of the function at A. No, I'm not asking you f of A. F of A could be different. How it could be different? Let me demonstrate it with some more examples. Let's say here, this is the graph of a function. Let me draw a graph of a function. So this is a graph, it breaks here and it goes from here like this. So this is how the graph of the function is defined and this is the point A. Now, if you start approaching A from the left hand side, it approaches this point. Let's call it L1. If you start approaching A from the right hand side, it approaches this point and let's call it L2. So are you not realizing that here, if I'm approaching A from left hand side and if I work on this function f of x, it gave me the value L1. This was the function, let's say f of x. And if I'm approaching A from right hand side on this particular function, it gave me a value L2. So I hope most of you must be realizing that in this particular case, L1 is not the value of the function at A. However, coincidentally or luckily, L2 happens to be a value of the function at A, but it is not necessarily true. That's exactly what I'm trying to make you understand. I'll give you one more example through which you may get more clarity. For example, let's say here we have another function. And let me draw its graph like this. Let's say this function goes like this and then this, and it is defined like this. So this is the graph of the function f of x, right? This is the graph of the function f of x. And this is a point A on the x-axis. I hope there is no confusion on it. Now, there are three things in this picture. What do I mean by three things in this picture? First thing which you all must have noticed is that this point, and of course, this point above here. I hope you all are understanding that this point above here is f of A. Will you not agree with me on this that, sir, if you approach A from the right hand side, this is the value which you'll get, let's call it L1. If you approach A from left hand side, you'll get this value, which is what I'm calling as L2. So are you not realizing that from A, if I look at A from left hand side, the function approaches L2. If I look at A from right hand side, then the function approaches L1. Did you get this part again? That limit x approaches A, its left hand limit, if I were to talk about which function, students, f of x, then its left hand limit when x approaches A from left hand side, it reaches L2. So I hope you're realizing it does not mean that this is the value of the function. It means where is it going? Where is it leading to? As long as, as soon as I start getting closer to A, where does the function lead me to? Where does the function go? Although it may not be L2 at A. At A, it could be something else. At A, it is F2, FA, which let's say I'm denoting by L3, which is completely different from L1 and L2. For example, here, limit x approaches A from right hand side on this function f of x. What do you understand by this? So when A is approached from right hand side, the function is approaching a value L1. Although it is not L1 at that point, but it is approaching L1. So here, it will be said to be L1. So that's your left hand limit, that's your right hand limit. But here, if I find out the value of the function at A, that is different, which I have denoted by L3. So I hope most of you must be clearly realizing, or rather all of you must have realized, that value of the function is a different thing, limit of the function is a different thing, and it should be understood with the help of the concept of limits. Did you get this particular part very clearly? I hope left hand limit, right hand limit, and everything is very well understood by you all. And these are the different possibilities as we have already discussed through the graph, as I have already shown to you. Some few things which you all should remember or understand is this, that first of all, remember that let's say there is a point here. Let me take a function, any function. And when I approach this point, let's say this point over here from left hand side and right hand side, let's say it is approaching a significantly high value. Even from left hand side and even from right hand side, from both these sides, it is approaching towards a significantly huge value, an amazingly huge value. And in that case, that at this point, the value of the function is not defined, although the function approaches a huge value, an infinite value. And that's where we say that if f of x, the limit of f of x when x approaches a is infinity. Let's say this point is a and this function is f of x. So f of x when x approaches a is infinity, then infinity means it is moving towards, it is tending towards, it is approaching a significantly huge value. Are you understanding the concept of infinity through the concept of limits? Now, moving ahead, let's try and understand this concept here from this example as well. Look at the graph of minus 1 by x for a while. Let's say I am drawing the graph of minus 1 by x. Now, if I draw the graph of minus 1 by x, I hope you must realize that in that case, this graph will be drawn like this only, below the x-axis, and in that case, as soon as x approaches 0, this graph will be approaching minus infinity. Are you getting it? So these are some simple observations which I'm trying to make you understand that what is the concept of infinity and what is the concept of minus infinity. I hope you are getting a great clarity on that front. For example, look at the graph of 1 upon x. Now, if I look at the graph of 1 upon x, when x approaches 0, from left hand side, the graph approaches minus infinity. But if x approaches 0 from right hand side, the graph approaches infinity. So are you understanding? If I'm asking you two things, let's say I'm asking you limit x approaches 0 from left hand side on which function 1 by x, then your answer will be minus infinity. Are you getting it? But if I write x approaches 0 from right hand side on the function 1 by x, then your answer will be plus infinity. Although equal to minus infinity and equal to plus infinity should not be written, because we cannot have minus infinity and infinity. We can always approach them. So there should be an arrow here instead of this equal sign. I hope you are understanding the concept of infinity and minus infinity. Did you get that part? I hope you have gotten a great and complete clarity on that. Now, there are some indeterminate forms which you should understand and study, that these are some indeterminate forms. We cannot determine them. We cannot find their values. But in the questions based on limits, we deal with such forms and then we solve these forms with some standard techniques. And those standard techniques are what we'll be discussing in this particular video. Here, look at this part. For example, if I take x square minus 1 upon x minus 1, limit x approaches 1. So when x approaches 1, if I simply put the value of x as 1 here, it will be 1 minus 1, it will be 1 minus 1. So numerator is also 0, denominator is also 0, and that makes it 0 by 0. That is an indeterminate form of 0 by 0. For example, here, if x approaches a, it is a minus a minus a. Basically, a to the power n minus a to the power n and upon a minus a. So 0 by 0. So this is a 0 by 0 indeterminate form. Similarly, the way we have 0 by 0, we may end up facing an infinity by infinity form as well. We will be someday facing infinity minus infinity form, 1 to the power infinity, 0 to the power 0, infinity to the power 0, infinity into 0. Please understand, don't assume that 1 to the power infinity should be 1, 0 to the power 0 should be 0, no, 0 to the power 0 could be 1, no, infinity to the power 0 should be 1, no, infinity into 0 should be 0, no. All of these values are indeterminate. You cannot find their values. Don't say that infinity upon infinity will be 1. No, you don't say that, because if you are saying that infinity will be a large value, then this infinity will also be that same large value. No, that's not true. This is a large value, this is also a large value, but are these large values same? No, that is not we are told. So you cannot cancel an infinity by infinity. Two infinities are not always same. For example, some of you might say that this infinity minus this infinity should be 0. Please understand, they are not the same two infinities. Infinity means a great value, a huge number. Now, which huge number? We don't know that. So conclusions cannot be drawn on these numbers. Please understand and remember them. I hope you will understand and remember these indeterminate forms. And now we'll discuss how do we deal with these indeterminate forms. As we have already discussed what is the meaning of the symbol infinity, and we have seen such scenarios here as well. What I am going to tell you first of all is that while dealing with the indeterminate form, 0 by 0 and infinity by infinity, there is a rule suggested by L'Hopital. L'Hopital was a French mathematician and he has suggested a rule. So L'Hopital is written like this, I think. And here in this L'Hopital, this H is silent basically. So L'Hopital was a French mathematician and he suggested a rule where whenever you deal with the 0 by 0 or infinity by infinity indeterminate form, then you can solve those questions through L'Hopital rule. Although we'll discuss all the standard techniques one after another, but in the beginning of this particular chapter or the concept of limits only, I'm introducing the concept of L'Hopital rule. What is it? How do we apply it? Let me take an example and make you understand this particular result here. Let me take an example here first of all. Let's say this is an example. Now in this question, what is the problem? If I replace x by 2 in the numerator and denominator, what do I get? So when you replace x by 2 in the numerator, 2 to the power 6 is clearly 64. I hope you understand. So 2 to the power 6 is 64 minus 2 into 24, which is how much? 48, and minus 16. Then what do we have in the denominator? Again, 2 is the limit. So when x cube has this 2 as x, so 2 to the power 3 is 8 plus 2 into 2 is 4 minus 12. Now what you must be noticing is that 64, 48 minus 16 is how much? 48 plus 6 is 54 plus 10 is 64. And this is also 12. So 64 minus 64 is 0 and 12 minus 12 is 0. So basically we are dealing with the 0 by 0 form. So whenever you deal with a 0 by 0 or an infinity by infinity form, there is a short technique, a shortcut to deal with such questions. Although it is not appreciated that you get addicted to this method, because this has its own flaws, it has its own demerits. I'll tell you in the later stages that where should you not use it, where should you avoid it. But if in case you can get questions, you can figure out the answers through this method, don't hesitate in doing it, because in the real examination hall we are solving MCQs, and if they can be done with the L'Hopital method, then you should have it. How? Let me try and do that. L'Hopital is a mathematician, said that here, whenever while solving questions based on limits, if you encounter either a 0 by 0 or an infinity by infinity form, then you can apply L'Hopital rule. So L'Hopital said that you differentiate the numerator separately and then you differentiate the denominator separately. What does it mean? You should not apply the quotient rule here. Don't say that P upon Q and quotient rule needs to be applied. No. What L'Hopital said, that if numerator is approaching 0 and if denominator is also approaching 0, or if both of them are approaching infinity, then it is said to be a 0 by 0 or infinity by infinity form. And in that case, differentiate the numerator and denominator separately. So if I apply L'Hopital, it says that first of all, apply the same limit here as well. And when you differentiate the numerator, what do you get? X to the power 6 becomes 6x to the power 5, minus 24x becomes minus 24. Denominator becomes 3x square, and there you have plus 2. Now what L'Hopital said is that try this 2 again. And if you could get some answer, that will be your answer. And if you again get a 0 by 0 or infinity by infinity form, then again apply L'Hopital. What does L'Hopital say? Differentiate numerator separately and denominator separately. But you should have a 0 by 0 or infinity by infinity form in order to apply L'Hopital rule. Did you get that? So here, if I'm applying or willing to apply the L'Hopital rule, let me check it whether it is giving me the answer or not. So here, if I replace this x by 2, 2 to the power 5 is 32. 32 into 6. So I'll be doing 32 into 6. So 6 into 3 is 180. 6 into 2 is 18. I hope there is no confusion on that. So I'm really sorry. 6 into 3 is 180. 6 into 2 is 12. I'm really sorry. So 180 plus 12 is going to be 192. So this is 192 minus 24, which is a non-zero value. So I think I'll get the answer in the next step. And here, if I replace this x by 2, 2 to the power 2 is 4. 4 into 3 is 12. So this is 12 plus 2, which is 14, right? So denominator has 14 here. What about the numerator? Numerator is 192 minus 20. So 192 minus 20 is 182, 172. And 172 minus 4 should be 168. Now further you can do it by yourself. I think from here it's easy to work out the answer. But mostly my concern was to make you understand that how do you apply the L'Hopital rule. Remember, in the questions of limit, this is a short technique which we have already discussed before discussing the different methods of evaluating the concept of limits. I repeat, Whenever you see a 0 by 0 or an infinity by infinity form, don't hesitate in applying it. But it has its own flaws and demerits, which we'll discuss in the upcoming stages. And there I'll show you that I'll of course demonstrate a lot of questions where we'll be having a 0 by 0 or infinity by infinity form. And there I'll tell you that don't apply L'Hopital. I'll show you that what are the disadvantages of applying L'Hopital. So there are a lot of other methods which we'll be using, and IIT-JEE is smart enough. They won't give you questions based on L'Hopital directly. Sometimes it can be used. You can get the answers. Don't worry about that. You should use it, but not always. And that's the problem. And of course, for that, we are going to discuss a lot of other methods as well to deal with a 0 by 0 or an infinity by infinity form. How? Let's explore that. But before I move ahead, I hope I have your assurance that you have understood L'Hopital. When should you apply it? How should you apply it? And how does it help in getting the correct answers? Now, moving ahead towards the next part, what do we have next here? I am, before starting to solve questions based on limit, trying to give you some standard expansions. These are the expansions which you must remember. In this one shot, we are first of all discussing certain expansions, which I am emphasizing and urging you all to have them at your fingertips. For example, if I talk about e to the power x, you should learn this expansion, which is called Taylor series as well. So e to the power x is always written as 1 plus x upon 1 factorial plus x square upon 2 factorial plus x cube upon 3 factorial, and so on until infinity. Please remember this expansion. Then this is one of those most important expansions you should remember or have in your mind. It's very simple to remember it. It's straightforward to remember it because 1 is there. It is basically x to the power 0 upon 0 factorial. Then this is x to the power 1 by 1 factorial. This is x to the power 2 by 2 factorial, x to the power 3 by 3 factorial. So if I were to generalize this, I could have simply written it like this, that you can write it as summation of x to the power r by r factorial, where r starts from 0 and it goes till infinity. This is also how you could write it. But of course, if you don't remember this result, I'll say that remember this pattern. I hope you'll have this thing with you. Along with this, yes, after e to the power x, the next most important is a to the power x, where a should be a positive real number. So what is the expansion of a to the power x look like? A to the power x is also a standard one. Here, what you do is you begin with 1, then you write x log a 1 factorial. Then you have x square log a whole square by 2 factorial. Then you have x cube log a whole cube by 3 factorial, and so on until infinity. And please understand, you got to remember them. You got to learn them. You have to have them at your fingertips. When I talk about the next expansion, this is binomial expansion, as we have already discussed it in the chapter binomial. If you wish to revise it, I'll show it to you again, that 1 plus x to the power n is written as 1. Then of course, nx by 1 factorial, then n minus 1 by 2 factorial whole times x square, then n minus 1 n minus 2 by 3 factorial whole times x cube. I hope you remember, this is basically 1. Then this is nc1 x to the power 1, this is nc2 x square, this is nc3 x cube, and so on. Where of course, this n has to be any real number and x should be lying between minus 1 and 1, or you can say that mod x should be less than 1. So these are some standard expansions, and there are a lot more which you should remember, because without these, you cannot solve questions based on limits. You will face a lot of problems. So to make your problems simpler, to have a great command over your understanding of this particular chapter, to be able to be more efficient in solving the questions, you should have these expansions at your fingertips. So before we actually start discussing this chapter, I am giving you some tools through which we'll be dealing with those questions, with those concepts. So the chapter hasn't exactly started in terms of discussing the different methods of evaluating the limits, but what is the prerequisite which is needed to be studied before starting the chapter. This is what we are discussing at this stage. For example, here, the expansion of log 1 plus x, amazingly important one. It is used in a lot of questions. I'll show you a lot of questions where we will require to write the expansion of log 1 plus x. Now, how do we write it? It is written as x minus x square by 2 minus x cube by 3 minus x to the power 4 by 4, where this x lies between minus 1 and 1. Right? This is how you write the expansion of log 1 plus x. Don't forget that. Similarly, here when you write the expansion of x to the power n minus a to the power n upon x minus a, In the chapter quadratic equations, I hope you must have remembered this, that x to the power n minus a to the power n is written as two factors of where one of them is x minus a and the other one was this only. So here, when I'm willing to write x to the power n minus a to the power n upon x minus a, then it is written as x to the power n minus 1 plus x to the power n minus 2 times a to the power 1 plus x to the power n minus 3 times a square and so on. Always remember that. The next result is this, that whenever you wish to write 1 plus x whole raised to the power 1 by x, there it is written as e to the power 1 minus x by 2, 11x square by 24 and so on. So far, I will still insist that these are the ones which you should have at your fingertips. Which one, students? This one, then this one, then this one. Of course, these are the ones which you already know. Then I'll talk about this one, then this one. At least these are the ones which you should remember. From here, all the three are equally important. All the three are equally important. You should have this expansion, sin x, cos x, and tan x at your fingertips. You should know it by all means. What do I mean by that? I'll begin with this. The expansion of sin x. I usually remember it like this, that all the odd powers of x appear with sin x. All the even powers of x appear with the expansion of cos x. What do I mean by that? Here, look at this. We know that sin x is an odd function. So if I replace x by minus x, it should be f of minus x. So that's exactly what it does. X upon 1 minus x cube upon 3 factorial plus x to the power 5 upon 5 factorial minus x to the power 7 upon 7 factorial and so on. So alternatively, plus minus sign keeps on changing. Similarly here as well, when you talk about cos x, it is 1 minus x square by 2 factorial plus x to the power 4 by 4 factorial minus x to the power 6 by 6 factorial. So I hope most of you, all of you must be clearly noticing this particular part, that here, that powers are odd with sign and powers are even with cos. Whatever power is there, that same factorial is there in the denominator, and the signs are alternatively plus minus plus minus. That is what is happening over here. I hope you will remember it. I have one doubt here. It should also be plus minus alternatively. So please make that correction. Although I'll verify and rectify it, don't worry about that. But here it should also be plus minus alternatively, which means if it is plus x, it should be minus x square by 2. Then this should be plus x cube by 3. Then this should be minus x to the power 4 by 4 and so on. Although I'll verify it, don't worry about that. But this is what we know about sin x and cos x expansions. This is something which you should remember at least until this power stage x to the power 7. Please remember it. You have to by heart it. You have to memorize it. The expansion of 10x, which is written as x, which is x to the power 1, then x to the power 3 by 3, then 2 by 15 times x to the power 5, then 17 by 315 times x to the power 7 and so on. But at least up till these 4 steps, you should have this at your fingertips. So these are the 3 which are very, very crucial ones. Along with this, of course, you should remember log 1 plus x. You should remember e to the power x. You should have these at your fingertips because questions are asked on these expansions. Of course, along with that, there are some more. For example, look at the expansions of sine inverse x. This is how you write it. The expansion of tan inverse x. This is how you write it. And the expansion of sec inverse x. This is how you write and remember it. So these are also some really important and crucial ones. Now, if I move ahead, these are also some standard expansions and you got to learn them by looking at them. Now, once we start discussing these different indeterminate forms, so what are these indeterminate forms? 0 by 0, infinity by infinity, and these standard 8 indeterminate forms are what we'll be discussing one after another, that how should you deal with them. For example, if I could begin with the first form. So these are some different limits. We deal with questions of algebraic limits. We deal with the questions of trigonometric limits. We deal with questions based on logarithmic or exponential, and there are miscellaneous forms. So the broader categorization now we'll discuss one after another through standard questions and their standard approaches, that what is needed to be done. For example, let's say if I'm dealing with a 0 by 0 form, so there are certain methods. For example, of course, L'Hopital is there for you. Of course, L'Hopital can be a savior, but it cannot always be used. It has its own demerits. That is what we'll be discussing in the upcoming. Because sometimes what happens is that you keep on applying L'Hopital time and again. So 0 by 0, then again you apply L'Hopital, then again you get 0 by 0. Then again you apply L'Hopital, then again you get 0 by 0. So you keep on getting. So it ends up consuming a lot of time of yours, the L'Hopital rule, and that's a problem here. So remember, you should be able to visualize and interpret that L'Hopital should be used or not. before applying the L'Hopital, you should be able to see the pattern, that whether it is actually giving you the answer quickly or it is consuming some more time. So you should be able to calculate or evaluate that effort. Now, how do we do that? From here, there is a standard formula which you should have with yourself, that whenever you deal with something like this, x to the power n minus a to the power n upon x minus n, as we have already discussed, the expansion of this, this is something we have already learned. So if you apply that expansion, x to the power n minus a to the power n, we know it has a factor x minus n. The other factor also we have had a discussion upon. So x to the power n minus a to the power n upon x minus a is expanded as, I hope you remember, we have discussed its expansion. I'll show you that expansion only first of all. So this expansion looks like this, and here when limit x approaches a is needed to be applied on this, I'll replace all these x by a, so they'll all become a to the power n minus 1, a to the power n minus 1, a to the power n minus 1 until a to the power a minus 1. And how many such terms are there? They are total n terms. So I am adding a to the power n minus 1 n times, which gives me n times a to the power n minus 1. That's exactly what I'm trying to give you here. That remember this as a formula, that whenever you deal with x to the power n minus a to the power n upon x minus a, then you replace it by n times a to the power n minus 1 whenever x is approaching a. This x must approach a. If I were to give you a simple example, I'll say, let's say, this question may appear in boards, but of course it won't appear in the IIT JEE. But to make you understand it very clearly, let's say I have x to the power 7 minus 3 to the power 7 upon, clearly, let's say x minus 3. Right, so I hope it clearly looks like a case where I'm dealing with x to the power n minus a to the power n upon x minus a. Now, what should be the answer? I hope everybody must have realized that, sir, answer will be pretty simple here. This x should be approaching a. A means what? A means 3. I have taken this 3 later. So this is the question, let's say. So of course, one of the ways is 3 to the power 7 minus 3 to the power 7 upon 3 minus 3. This is a 0 by 0 form. Can I apply L'Hopital? Yes, you are free to do that. What does L'Hopital say? Differentiate numerator. So the differentiation of numerator says, of course, this limit which says x approaches 3, x to the power 7 is 7x to the power 6. This being constant becomes 0. This is 1 minus 0, so upon 1. So this is exactly nothing but what? N a to the power n minus 1, that formula. So did you get it? That here in this category of questions, whether you use the formula or L'Hopital, both are equally important and workable. So here, I hope you can replace x by 3 and you get the answer, which is going to be 7 into 3 to the power 6. So this particular formula, you should remember. I won't be applying it like this. Questions won't be directly visible on based on this concept like this, but you should have this thing in mind, that this limit holds this as a value. If you forget it, you have the L'Hopital, apply it and get the answer. Don't hesitate in doing that. Did you get that part? So even if you forget some formulae, L'Hopital is there as a savior. Now, if I go back to the discussion we all were having, this is what I was trying to give you, that in 0 by 0 form, there are two methods. The first method is factorization and the second method is rationalization. I'll try and tell you through an example that how do we deal with the 0 by 0 and infinity by infinity form through factorization and rationalization through a question. But before I move to a question, I'll like to show you this form as well, that whenever you deal with a to the power x. So we know a to the power x has its own functionality. What do I mean by that? A to the power x has two versions of its graphs. What I'm trying to make you understand is, let's say I'm dealing with the function a to the power x. And there are two cases. Which two cases? In the first case, when a lies between 0 and 1, and the second case, when a is greater than 1. We know that when a to the power x function is taken, a is always positive and a is never 1. And we categorize into two categories where a is between 0 and 1, and second case when a is greater than 1. Do you remember that? We had a discussion on this when we discussed logarithm and when we discussed functions. Now, whenever a is between 0 and 1, if you draw its graph, it is a decreasing function like this. I hope you remember it. But whenever a is greater than 1, it is an increasing function like this, an exponential function's behavior it shows. Now, why am I discussing all this? I am trying to give you a very simple observation. Let's say this is the graph of a to the power x. So when x approaches infinity, this is of course x-axis. I hope you can see it very clearly. So when x approaches infinity, are you not seeing that this function is approaching 0, because this is becoming slightly smaller as soon as x is approaching infinity? So when x goes high, this a to the power x approaches 0 and it becomes 0. So I repeat, if a is between 0 and 1, and if I apply limit x approaches infinity on a to the power x, it approaches 0. But what is the catch here? The catch is when x approaches infinity, in this case, when a is greater than 1, are you not seeing that a to the power x is also approaching infinity because it is becoming significantly higher as x is also increasing. So if x is approaching towards infinity, a to the power x also approaches infinity. So what does it mean? If I say limit x approaches infinity on a to the power x, then it will be infinity. It will be approaching infinity. Did you get that part? I hope you are able to understand this without any hesitation. Sometimes what students do is that, sir, what if a is 1? So if a is 1, it becomes a constant function. If a is 1, it becomes a constant function. Constant functions means what? If a is 1, it is going to be 1. So f of x is going to be 1. So when x is approaching infinity, if x is approaching infinity, this is still approaching 1 only because this function is staying at 1 only. So if a is 1 in a to the power x, if a is 1, and if I apply limit x approaches infinity on a to the power x, then I'll say it will be approaching 1. Did you get that part? It will be approaching 1. Why? Because a is 1 in that case, and this has become or gotten converted into a constant function. So it will always remain 1 no matter what value of x you take. So even x is approaching a slightly or amazingly huge value, then also a to the power x will be approaching 1 when a is 1. So these are the three cases. Did you get that part? This is that exception here. So that's exactly what I was trying to tell you through this particular scenario. I hope you have gotten a great clarity on it. So this is the conclusion that when x approaches infinity, a to the power x shows three behaviors. If a is greater than 1, it will be infinity. If a is equal to 1, it will be 1. And if a is between 0 to 1, it will be 0. There are three more conclusions which I'd like to show you here. Which students, for example here, look at this. What if x is approaching minus infinity? So when a is between 0 to 1, these are the cases regarding to this only. So if x is approaching minus infinity, what can you say about a to the power x? Would you not say that in a to the power x, if x approaches minus infinity, I can see that this function is approaching infinity? So I'll say that this is approaching infinity when x is approaching minus infinity in a to the power x when x is approaching minus infinity and a is lying between 0 and 1. But what if I look at this part? What if x approaches minus infinity at this front when a is greater than 1? In that case, I can see that a to the power x is becoming as low as possible and it is approaching 0 in that case. So what I'm trying to make you understand is that here in this case only when a is greater than 1, limit x approaching minus infinity, a to the power x will be 0. Whenever a is greater than 1, are you not noticing it? Are you completely getting it? Are you able to digest all what I'm trying to say here? So through graphs, you can generalize this, but these are some standard decent results which you should have in your mind. Did you get that? Of course, there are standard forms we'll learn, of course, don't worry about that. But this is a generalization which I want to give again through this particular method. Now, what is that generalization? Let's say I'm having two polynomials. The numerator has a polynomial in degree m, the denominator has a polynomial in degree n. I'll take certain examples to give you more clarity on this. Let's say numerator is 3x to the power 6 plus 4x to the power 5 plus let's say 7x to the power 4 minus 3x cube plus 2x, although you need not write all this. But I'm just trying to give you the idea that this is a polynomial of degree 6 in the numerator. And there is a polynomial of degree 3 in the denominator. Let's say it goes like this, 2x to the power 3 minus 3x plus 1. And what you have is the limit when x is approaching 0. So most of you must be thinking that, sir, when x approaches, the limit when x is approaching infinity, it's not 0, x is approaching infinity. So the moment you see x is approaching infinity, this will be infinity upon infinity form, because when you replace all x by infinity, it becomes completely huge and it is also huge. So infinity by infinity can be solved with the help of L'Hopital. But even if you apply L'Hopital, do you not think that, sir, this will vanish because it has degree 3? But it won't vanish. If you keep on applying L'Hopital, because every time you apply L'Hopital, you will keep on getting infinity by infinity form. So through L'Hopital, are you not understanding that this denominator will get vanished very soon because it has degree 3? With 3 derivatives, it will get vanished, but this won't vanish. And that's where I'll say that the answer is going to be infinity. If you don't trust me, if you don't believe me, you apply L'Hopital once. This will be a polynomial in degree 5 after first phase of L'Hopital, and this will be a polynomial in degree 2. Then you apply L'Hopital once again because you are again facing an infinity by infinity form. This will become a polynomial in degree 4. This will become a linear polynomial. Then again you apply L'Hopital. This will still remain a polynomial in degree 3, and this will become constant. So a polynomial in degree 3 divided by constant, and x is approaching infinity. So infinity cube by constant, that is going to be infinity. Did you get that part? So are you realizing that whenever you see two polynomials where the degree of the numerator is greater than the degree of the denominator, then this always approaches infinity. Will you remember it? But of course, there you need to understand that these coefficients here, it should have been b naught. So let me just rectify that correction here. Just give me a second, students. Here it was b naught basically. This is b naught. So what you need to understand is whenever a naught and b naught are positive, whenever a naught and b naught both are positive or both are negative, which means their product should be positive if both of them are negative or both of them are positive. So if the coefficients of the highest degree term, if the coefficient of the highest degree term are either both positive or both negative, in that case, please remember, if the numerator's polynomial degree is greater than denominator's polynomial degree, in that case, the limit is always infinity. So instead of evaluating it, you can always say the answer is infinity. Why? Because look at this 3 and this 2. The coefficients are both positive, or if both are negative, then we say the answer is infinity if the numerator's degree is greater than the denominator's degree. Did you understand this part? So you need not evaluate it. You can always mark infinity as the correct answer. These are the short techniques I'm giving you directly. You can use these results. Now, let me take or talk about another result. When do we have it as minus infinity? For example, the numerator has a degree 3x cube plus 4x minus 7, right? This is a cubic. And let's say denominator is a linear, which is, let's say, minus 4x plus, let's say, 3. And here, again, x is approaching infinity. So what you need to understand is, again, the numerator, the polynomial in the numerator has greater degree or the larger degree than the polynomial in the denominator, because cubic polynomial is given in the numerator and linear polynomial is given in the denominator. So we know that the answer is going to be either infinity or minus infinity. But here, if I look at the coefficients, if I notice the coefficient, it is positive and it is negative. So if they are opposite in sign, if one is positive, other is negative, or the numerator is negative, the denominator is positive, the coefficients of the highest degree term, in that case, we say that this will not result into infinity, rather this will result into minus infinity. So this scenario will give me the answer as minus infinity. Did you get that part? So these are some standard results which I'm asking you to memorize directly. Now, let's talk about these results. When do we apply these results? Please understand, the third result is, let's say the numerator has a polynomial 2x square plus 5x plus 6. The denominator also has a polynomial, for example, 6x to the power 4 plus 7x cube minus 3x plus 2, right? So this is a polynomial, basically a rational polynomial in the numerator and denominator, and x is approaching infinity. Now, what do we say? Remember, if the degree of the numerator is less than the degree of the denominator, what you must notice is that this will be huge, this will be very small. Something very small upon something very huge is always approaching 0. If you don't get it like this, you can apply L'Hopital. What do I mean by L'Hopital? L'Hopital says that, sir, first when I place x by infinity, it will be infinity by infinity form. So I'll apply L'Hopital. I'll differentiate this and I'll differentiate this. So on differentiation, this will become a linear and this will become a cubic. Then again, I'll differentiate because again, I'm getting infinity by infinity. So this linear will become constant, but this will become a quadratic. So constant upon quadratic. I'll again put x is equal to infinity here. So constant upon infinity. So constant upon infinity is always 0. I hope you remember. So it approaches 0 in that case. That's exactly what I'm trying to give you. That if the degree of the numerator is less than the degree of the denominator, then the answer is 0. Remember, when you have this x approaching infinity, don't forget that. Now the most crucial result. It is a naught upon b naught if both the polynomials are of the same degree. What I'm trying to make you understand is, let's say here we have 2x cube plus 3x square minus 6x plus 5. And the denominator says it is minus 18x cube plus 9x square minus 5x plus 3. And here again the limit x approaches infinity is given. Now most of the students, what they do is they start either factorizing or rationalizing. Rationalization wouldn't work. Factorization you may or you may not able to do. So how do we do it? How do we solve it? So in that case, don't do anything. Not even L'Hopital. Don't even apply L'Hopital, because even if you apply L'Hopital, you'll have to apply it 3 times. I hope you're realizing why. So instead of even doing it all like this, there is a short technique, there is a standard technique. What is that? Let me try and tell you that. Here, have you noticed that the degree in the numerator and denominator is same? So whenever the degree in the numerator and denominator is same, the answer is the ratio of their coefficients. The answer is the ratio of their coefficients. The answer is the ratio of their highest degree terms coefficient. So x cube has 2 here, x cube has minus 18 here. Your answer will be minus 2 by 18. That's it. Can you believe this? How? I am not telling you how. I'm just giving you the hint or the idea. Apply L'Hopital 3 times, you'll get how. So every time when you do this, you may use that entire lengthy cumbersome process or something like this, which is a very straightforward result. So will you remember it? I'll take one more example to consolidate it so that you keep this result with yourself. For example, here I have 2x square plus 3x plus 5 whole divided by minus 6x square plus 2. I hope you remember that the limit should be infinity. X should be approaching infinity. In that case, have you all noticed that the degree in the numerator and denominator is same because both of them are quadratic? So we know that if x is approaching infinity, the answer is the coefficient of their highest degree terms, which is nothing but 2 by minus 6. So the answer should be minus 1 by 3. Will you remember this result now? This is a short technique, you may say, but you may use L'Hopital, you may use factorization, but this is the standard result which I'm giving you. And that's exactly what I want to give you in this chapter. There are a lot of standard results, although we use expansions a lot many times because that is something very important. So even before starting this chapter, in the beginning of this chapter only, we have discussed the prerequisite where we have been discussing that how should you remember the different expansions. Don't forget the expansions are very crucial, and that's exactly will play a very crucial role here. Now, if I move towards the next part, what do we have? This is a question. This is what will solve through rationalization because this is an infinity by infinity form. Before I do it, can you try solving it by yourself? Let's see how many of you do it. This is the category of questions they keep on asking. For example, JEE Mains 2021. So they make you solve something like this where they give you some unknowns, some arbitrary constants, and then they ask you the values of those constants. Now, how do we deal with this category of questions? Let's have a look at that. So here, this is something we are given. Now, again, if I replace x by infinity, this is infinity minus infinity form. Now, how do I convert infinity minus infinity into something solvable, which we usually deal with as 0 by 0 or infinity by infinity? So what I'll do is I'll use rationalization here. How? Let's have a look at that. So the conclusion is, the question is that it is under root x square minus x plus 1 minus ax, right? That is what we have. So if I multiply and divide it by the conjugate of it, you can directly do it. I'm doing it for you for the first time, so I'm writing all the steps very clearly, but you can directly write the next step. That is how you should solve questions, right? In the denominator, I'll be seeing the conjugate of it. It will be, which will be x square minus x plus 1 plus ax, and of course the same should be multiplied in the numerator as well, x square minus x plus 1 plus ax. Did you get that part, students? I hope there is no confusion on that. And here the limit is x is approaching infinity. Okay, now this is something which we are already given as b. Okay, so we'll try this b, we'll work out this b later, but first of all, let us look at this particular part. I hope you know that a minus b, a plus b is a square minus b square. So the result in the numerator will look like x square minus x plus 1, x square minus x plus 1. This needs to be squared and it gives you x square minus x plus 1. I hope there is no doubt or confusion on it. Minus a square x square. So this is minus a square x square. The denominator stays as it is, the way it is given over there. It is clearly x square minus x plus 1 in the denominator plus ax. Plus, of course, what is wrong with this? Plus ax. And on this entire expression, I'm putting a limit, which is x approaching infinity. Now, what's the problem here? Let's try and identify the problem. The problem is that if I look at that logic of polynomials in the numerator and denominator, this is something finite. This is something significant. This is something which is given to us as an answer, which means this is solvable. This should have a finite answer. As you can see, b is a finite value. A comma b is not a range. It is not an interval. It is a set of a pair of two values, a comma b. A and B have two values, distinct or same or whatever values they have. So that is that pair, right? Now, if I look at this part, the problem here is if I could rearrange this, x square minus x plus 1 minus a square x square. Look at the numerator. Can I rearrange that numerator? If I rearrange that numerator, how will it look like? So x square minus a square x square. If I take x square common, I'm left with 1 minus a square. So here I'm left with 1 minus a square times whole of x square. Did you get that? Now from there, I'm left with minus x plus 1. So this leaves me with minus x plus 1 in the numerator. What do I see in the denominator? It gives you x square minus x plus 1 plus ax. So it is x square minus x plus 1, x square minus x plus 1, and then plus ax. Now I'll tell you the problem here. What do we have? Sir, as per the question, that x approaches infinity. Now imagine this is the numerator, which is a quadratic, degree 2. This is the denominator, which is a linear expression, because even if it is degree 2, because of this under root sign, this can be treated as a linear expression. So denominator is a degree 1 expression, numerator is a degree 2 expression. So higher degree upon lower degree approaches infinity. Do you remember that conclusion? We had a discussion on that. And that's a problem, because in that case, this will become infinity. This limit will result into infinity. But it is given to be something finite. So if it is finite, then I should have this numerator and denominator's degree should be same. The degree of the numerator and denominator should be same. So how can I have that? Sir, if by some means the numerator also becomes linear, because the denominator cannot increase its degree. So the numerator has to boil down its degree. So numerator is quadratic. Can I make or convert it into a linear? Yes, there is a possibility. How? If I could vanish this x square, if I could remove this x square, how can we remove this x square? Sir, the coefficient of x square, which is what? Sir, the coefficient of x square is 1 minus a square. So if 1 minus a square becomes 0, then x square term will get vanished and I'll have a linear expression in the numerator. I'll have a linear expression in the denominator. Did you get that part? Are you able to understand it? Now, how do I solve this particular expression now? So I think if 1 minus a square is 0, we know a square is 1, and from here I can conclude that a will be plus minus 1. A will be plus minus 1. Did you get that part? I hope there is no confusion on that front. So whenever a is plus minus 1, this will become 0. So now my question becomes minus x plus 1 in the numerator, and the denominator is under root over x square minus x plus 1 plus of course ax. And of course, the limit here is x approaching infinity. Now, how do we solve questions based on this category? If you get stuck, if you ever get stuck and if you want to get rid of this expression, the best method is try to convert these x into 1 by x. Try to bring these values which are approaching infinity into 1 by x form so that they start approaching 0. How do we do that? See, both are linear. Both are linear. So my approach will be saying that take x common from the numerator, take x common from the denominator. So what is the advantage of it? Instead of having infinities now, I'll have zeros now. What do I mean by that? Let me try and demonstrate it. For example, here limit x is approaching infinity. I'm taking x common from numerator and denominator. So this becomes minus 1 in the numerator. This becomes minus 1. And what does it become? This becomes 1 by x. Similarly, from denominator, if I'm taking x common from here, it will be a only. It will be a only. Of course, this a is either plus 1 or minus 1, which I'll tell you which should it be, which it should not be, which it cannot be. We'll discuss that later. And then plus. I am taking x square common from here inside that under root sign, and then x will be taken out. And that x, this x and this x common from the numerator will get cancelled. So I'm not writing that part. So from here, when I'm taking x square common, it is 1 minus 1 by x plus 1 by x square. Did you get that? So it is under root over 1 minus 1 by x plus 1 by x square. And that's how you simplify this. Did you get that part? I hope there is no confusion on it. Now, why did I do it? When you do that, all these values will now approach 0, because when x approaches infinity, 1 by x square will approach 0. And that was the motive. So when you do so, The final conclusion which you receive is, I hope you can see in the numerator it is -1 plus 0. So it is -1. In the denominator is a plus 1, 0, 0. So it is under root over 1, which is 1. That's my final answer. But the problem is, can I take the value of a as -1? Because if a becomes -1, this is -1 upon 0, which is infinite, but b is something finite. So from here, I'll say the value of a will be 1 because a cannot be -1, it is discarded. So we have finalized a value of a which should be 1. Did you get that result? Now, once I have finalized the value of a as 1, I'll say if I have a as 1, it should be -1 upon 1 plus 1, which is 2. So my answer to this final question will be -1 by 2, which is the value of b. Which is the value of b. So we have received a as 1 and b as -1 by 2. So 1 comma -1 by 2, which we are given in option A. Did you understand the whole process? Did you understand the entire algorithm? Were you able to make some sense out of it that we were dealing with an infinity minus infinity indeterminate form? How did we convert into an infinity by infinity form? Then how did we convert into a standard result, which we have discussed, a polynomial upon polynomial, something related to that. And then, of course, we could conclude the values of these arbitrary constants through our intuition, through our standard deductions. Did you understand the whole process? I hope you are able to make a lot of sense out of it. You were able to get some lot of conclusions out of it. And that's exactly what I was trying to give you here. These results are some standard results which you should have at your fingertips. You should memorize them. Of course, with certain practice, students learn it, but still, if you don't know them, this is the opportunity, learn them. The first one is sin x upon x. As long as x is approaching 0, this is 1. There are a lot of methods. Do you remember we had a discussion that in trigonometry, I have shown you the graph of sin x, tan x and x. I hope you remember. If I could give you a closer perspective, that this is the graph of sin x, right? This is the graph of sin x. And if I could draw the graph of x, this is how we have seen the graph of x. So when x approaches 0 from left hand side and right hand side, sin x and x are almost equal. They are overlapping each other. So that's why even tan x is also equal. So that's why we say sin x upon x, tan x upon x, sin inverse x upon x, and tan inverse x upon x. This all results into 1 when x approaches 0 from left hand side or right hand side. Did you get that? Did you understand that? I hope you'll remember it. If you don't remember it, you can apply L'Hopital as well. Through L'Hopital also, since it is 0 by 0 form, sin 0 upon 0, this is 0 by 0. You can apply L'Hopital. Derivative of sin x, cos x upon 1. Cos x upon 1, which is cos x. When x approaches 0, cos 0 is 1. Through L'Hopital also you can reduce it. But this is such an easy result that you should have it at your fingertips. This will be used at a lot of places. Only thing you should remember is the value which we are writing here, that same value should be there in the denominator. The angle which you are writing here, that same value should be there in the denominator. Even you should remember that if in the numerator it is degree, the denominator should have it in degrees. If the numerator has it in radians, the denominator should also have it in radians. I hope you are understanding it. And the same is true for sin inverse x upon x and tan inverse x upon x. So do remember it. All of these limits will lead us to 1. Remember this as a crucial result, because this is something which is also asked at a lot of places or used at a lot of places. The same will be true here. Now that's exactly what I was trying to give you, or saying or mentioning, that here, look at this. This is sin x degree upon x. Now the problem is this is x degree, but denominator is x radian. So can I convert x radian into degree? I hope you haven't forgotten. In Trigo, we had a discussion that 180 degree is equal to pi radian. So do you remember that from here, I would say that 1 radian will be 180 upon pi degree. Do you remember that? So here, if I wish to convert this x into that, something like that, I'll multiply it by 180 by pi. So that becomes 1 now, and that multiplication product gives you pi by 180 here. Did you get that part? The same result will apply here. See here. In this case, x is approaching a. So this a minus a is approaching 0. This a minus a is approaching 0. That's how it is becoming 1. The same is true here as well. So I hope there is no confusion or doubt on that front. Now, moving ahead with that result, I hope there is no confusion on that part. How did we convert this degree into radian? I hope you have gotten a great and complete clarity on that front. That 1 radian will be 180 by pi degrees. And by that, I have converted it into this result. Now, moving ahead, let's try a question and get more clarity on whatever we have discussed and learned so far. Although I have given you a lot of theory initially in the beginning, and now we are going to get or start applying those learnings. For example, look at this question. This is a classic example of expansion or the Taylor series which we have learned. I have asked you, I have very strongly urged you to remember the expansion of sin x, cos x, tan x, to expansion of log 1 plus x e to the power x. Those expansions are amazingly useful, and those expansions are very widely used in the questions based on limits. Of course, there can be multiple approaches through which you can find the answers, but through those expansions, you can very directly and very easily and more effectively find the answers. How? I'll show it here. I'll demonstrate it here in this particular example. See, we are told alpha, beta, gamma are real numbers. Okay, they are three real numbers. That's fine. Now, this is an expression which is having a finite limit 3, and there x is approaching 0, and we are seeing alpha, beta, and gamma written over there. And then something related to alpha, beta, gamma is asked, which we can find out once we have figured out the values of alpha, beta, and gamma. How do we solve it? I'll say use the expansion of series. So which all expressions are given here? I am seeing sin x, I am seeing e to the power x. So basically, if I know the expansion of sin x and e to the power x, I would be able to do it. So if I could take you towards the expansion of the Taylor series, I'll try and show you those expansions first of all. So I hope you remember, we have seen the expansions in the beginning of this lecture only. So where were they? Here. First of all, I'll talk about the expansion of sin x. Do you remember odd functions? So x to the power 1, x cube, x to the power 5, x to the power 7. So powers will be odd. This is how I personally remember them. Then alternatively plus minus. And then whatever is the power of x, that same factorial is given in the denominator. I hope you have understood the expansion of sin x. Now, when I talk about the expansion of e to the power x, do you remember e to the power x? This is the generalization we have discussed. X to the power 0 upon 0 factorial plus x to the power 1 upon 1 factorial plus x square upon 2 factorial and so on. And that's how we have written the expansion of e to the power x. These two standard results I'll be using here in this particular question. I hope you haven't forgotten them. Just give me a second. I'm bringing it right there in front of you. So here it is. Now, how do I write it? First of all, this is x square. So the question says limit x approaches 0, right? The numerator has x square. How do you write sin alpha x? See, we know the expansion of sin x, but if in case alpha, in case of x, instead of x, we are dealing with sin alpha x. So all I need to do is replace that x by alpha x. So how do I begin with? Initially, we have alpha x to the power 1. So it will be alpha x to the power 1. Then I'll use minus sign. Then it will be alpha x cube divided by, alpha x whole raised to the power 3 divided by 3 factorial and so on. And there will be higher degree terms. So I think that will overlap there. So I think I need to write it a little bit here. So just give me a second, students. I'll write it somewhere here. So I think it will be more useful. So this is limit x is approaching 0 because this is going to be huge in terms of expansion. So x square remains as it is. Then you have sin alpha x. So I'll begin with alpha x to the power 1 minus alpha x whole raised to the power 3 by 3 factorial plus alpha x to the power 5 and so on up till infinity. Did you get that result? Plus gamma minus 1 plus gamma minus 1. Okay, gamma minus 1. Then I'm going to write the expansion of e to the power x square it is. So if it is e to the power x, we know the expansion. So in those x, I'll replace those x by x squared. That's the only change. So I begin with x to the power 0, that is 1, plus x upon 1 factorial, but x is x square here, so it should be x square to the power 1 by 1 factorial. Then the next term will be x square to the power 2, which is x to the power 4 by 2 factorial and so on until infinity. Do you understand this? Did you get a complete clarity on this? Whole expression divided by sin 2x. I hope the way we have written alpha x, in the same fashion we'll be writing sin 2x. So it will be 2x, then 2x whole raised to the power 3 divided by 3 factorial and so on, right? Then minus beta x. So we have this minus beta x. Now the result which we discussed initially, x approaching infinity or x approaching 0 and two polynomials are given. Now, are you not saying that same case is getting generated here? So that's the point I was trying to give you, or asking here. In this case, you should use your intuition. If there is an answer exists, then what should all happen? I'll rewrite this part for clarity, although a lot of students from here only can get the answer. But if you get confused, I'll ask you a very simple result, that club the terms with same powers. For example, in the numerator, if I ask you, can you see any constant term? Yes, you must be agreeing that there will be constant terms. There will be terms with higher powers of x which will be there in numerator and denominator, but let us look at some standard decent lower powers of x. For example, here, if I look at the power of x, which is what, let's say, if I begin with the constant term. So from here, I don't see any constant term appearing, but from here, gamma minus 1 plus 1, that will be the first constant term. So I'm writing that first constant term here. So the first constant term will be gamma minus 1 into 1, where we know that x is approaching 0. I hope you haven't gotten confused on that, right? Now, let me move ahead. So that's your first term, gamma minus 1 into 1. Now, let me look at the coefficients of x square. I hope you all are realizing that this is only where you are getting the coefficient of x square, because here, x square into x will give you a term in x cube, right? So the coefficient of x won't be there. So the next term will be having coefficient in x square, which is gamma minus 1 into x square. So the next term will also going to be is going to have gamma minus 1 as its coefficient and x square as its term, x square times gamma minus 1. Did you get that? Now let's look at the term in x cube. I hope you must be realizing x square into alpha x. That will be a term in x cube. So it will be alpha x cube. So this will be alpha x cube. No other term will give me x cube, because here it will be x to the power 4 next. And here again, x square into x cube will be x to the power 5. So I'll keep getting higher powers of x. For example, x to the power 4, x to the power 5, and so on. So apart from x cube, I'll start getting higher powers of x in the numerator. Did you get this part? Are you having a great clarity on this? Now, let us look at the denominator. If I look at the lowest power here, I have 2x minus beta x. So I'll say that it is 2 minus beta times whole of x. So it is 2 minus beta times whole of x. Then what do I have next? The next term is minus 2x cube upon 3 factorial. So 2 cube we all know is 8. 3 factorial is 6. So 8 upon 6. I hope there is no confusion on that. So it is 8 upon 6, and 8 upon 6 is clearly 8 upon 6, right? So 4 by 3. Did you get that? So this is going to be minus 4 by 3 x cube. So this is going to be minus 4 by 3 x cube. And then I'll be seeing a lot of terms with higher degrees in x. Did you get that part? 2x minus beta x, which I have written as 2 minus beta times whole of x. And then I had minus 8 by 3 factorial, which is minus 8 by 6, which we write as 4 by 3 x cube. So that is what we have written. Now what do we do? Now please understand, if I replace x by 0 over here, if I replace x by 0 over here, the problem will be, I hope you all are noticing here, if I replace x by 0 here directly, all the terms here will become 0. All the terms here will become 0. So this will be something constant upon 0. Are you not noticing it? This will be something constant upon 0, and something constant upon 0 reaches infinity. So my answer will be infinity, but the problem is this is not infinity, this is something finite. So the answer is something finite. Did you get that? So to have a finite answer, what you should here have is that, sir, something, first of all, this expression should be something constant. The denominator cannot be 0. So the denominator, first of all, should not be 0. Okay, we'll try to have it. But before I do that, do you not all agree that, sir, this expression should not be there? Because if I could remove this, if I could simply remove this particular result, let's say this is not there. Imagine that this is not there. Then this x are all cancelled, and then I'll be left with something constant in the denominator, and that will ensure that the denominator will not be becoming 0. Are you understanding how am I thinking? And that same mindset is needed here in this category of question. So first of all, I should get rid of this constant term, because when I do so, when I get that, I will ensure that this x, a lot of x are cancelled, and I have a constant term in the denominator, and the denominator won't be becoming 0. That's the second prerequisite we have. So first of all, I need to remove this gamma minus 1. So how can I ensure that this gamma minus 1 is removed? So to remove gamma minus 1 should become 0, which means gamma should become 1. So first conclusion is that when gamma is 1, I think my question becomes more solvable. Because if gamma does not become 1, this will be 0, this will be constant, and constant upon 0 will reach infinity. And that is the answer. The answer is 3. Something finite. So are you understanding? First of all, gamma should be 1. So the moment gamma becomes 1, this omits. And the best part here is, the moment it is omitted, this is also omitted, because gamma is 1, so 1 minus 1 is 0. So what do we see in the numerator now? Now the numerator becomes limit x approaches 0. This is omitted 0, this is also omitted 0. So technically, now what am I left with? See, the moment you see gamma becoming 1, all of this is removed. all of this is removed. So technically you are left with this expansion or this expression only. Did you get that part? Are you getting more clarity on this? So my question boils down to this upon this. I hope you are having a great clarity on this. Now I'll simply write it here only. So this has removed, this has removed. I'm left with alpha x cube and some higher degree terms. So next term will be x to the power 4 and so on. Some higher degree terms in x, right? Divided by here. Now what do we have here? It is 2 minus beta times x. It is 2 minus beta times x plus, sorry, it's not plus, it's minus 4 by 3 times x cube and so on, right? What you all must be noticing is that, sir, one x can be taken common and that x can be cancelled by this x. I hope that result you all are able to understand from here. So if I'm able to remove that one x common from that, take that x common from the numerator and denominator, and I could remove it, the question now looks like limit x approaches 0. This x is removed, so it is alpha x square and some higher terms in x divided by 2 minus beta constant minus 4 by 3 x cube. Sorry, it's not x cube now, it is x square and some higher degree terms in x. Did you get that result? Now, if I remove or replace x by 0, the problem is going to be, see, this 0 will make the entire numerator 0 divided by something constant. So are you not noticing the problem again? 0 upon constant will be 0. So the limit will result into 0. But is this limit 0? No, this limit is neither 0 nor infinity. It is 3, something finite, and 3, non-zero. So if it is 3, which is non-zero, I should not have this getting created over here. How can I get rid of it? Sir, if by some means both numerator and denominator become the polynomial in same degree, then I'll have this conclusion where this constant term should be removed. There is no constant term in the numerator now, so it will be becoming 0. The denominator will also be becoming 0 except for this part. So if this part is not there at all, imagine that this part is not there at all. If this part is not there at all, this x square and x square will get cancelled and I'll be left with some constant terms, and that could be the answer. Are you understanding how am I approaching this question? So my next omission will be that yes, 2 minus beta shouldn't exist. 2 minus beta must not exist. So my next conclusion is that 2 minus beta must not exist, which means it should be 0. Now, if 2 minus beta becomes 0, beta becomes 2. That's my second conclusion. Did you get that part? I hope there is no confusion on that. The moment 2 minus beta becomes 0, what am I now left with? I am now left with alpha x square plus higher degree terms in x divided by, this is 0. So you are left with minus 4 by 3 x square and some higher degree terms in x. So all of these terms contain x, right? Limit x approaches 0. I hope x square can be taken common. So in the numerator, we will be left with alpha plus some high degree terms in x divided by minus 4 by 3 x square is cancelled plus some high degree terms in x where limit x is approaching 0. Now I'm seeing that all of these terms which are higher degree terms in x will become 0. This is also becoming 0 because all of these terms contain x. So this is what I am now left with. What am I now left with? I am now left with alpha upon minus 4 by 3. Alpha upon minus 4 by 3, which I can write as minus 3 alpha by 4. Did you get that part? But this answer is not the answer. According to them, the answer is 3. So the answer which we have received should be equal to 3, which is given in the question. Did you get that part? So if I could compare it, I have cracked the value of alpha as well from here because 3 gets cancelled by 3. So alpha should result into minus 4. So I think we have all the three values, alpha, beta and gamma. So alpha is minus 4, beta is 2, gamma is 1. Minus 4, 2 and 1, right? So we have, I think 2 plus 1 and minus 4 is plus 4. So it should be 7, which means option A. Have you gotten a complete clarity on this category of questions which was asked by JEE Mains last year? We have used simple expansion technique, Taylor series, and then through these intuitions that the answer should exist. Some things should be eliminated. Some things should not be there. So we kept on eliminating them. For example, we eliminated first of all the constant term in the numerator and then the constant term in the denominator. Then the numerator and denominator became same polynomial. They have the same degree terms. So x square both were there. So that x square got cancelled. We left with some constant terms because the other terms of high degrees of x became 0 because x was approaching 0. So I'm left with these two constant terms. Their ratio would be the answer. And that was 3 given to us. So that's how we could crack beta, gamma and alpha respectively. Did you get that part? I hope there is no confusion on that. Now, if you have understood that front, let me move ahead towards the next portion over here. Now we'll understand how to expand questions based on logarithmic series. My only concern is that you should remember this. If you remember this, the job is done. Log 1 plus x has its own expansion, the Taylor series, as we have already discussed it previously. Alternatively, plus minus sign. So x minus x square by 2 plus x cube by 3. Then you have a minus sign here. It should be a minus sign over here. And then alternatively, plus minus sign keeps on appearing. But my concern here is that are you understanding log 1 plus x expansion, the expansion of log 1 plus x? And do remember, log 1 plus x upon x is always 1. How? I hope you can see. Of course, when x approaches 0. It is basically nothing but what? I hope you can see. You can use apply the L'Hopital rule, because when you replace x by 0, this is log 1 by 0, which is 0 by 0. 0 by 0 means what? L'Hopital. So you can differentiate it and get the answer. Or if you don't know that, you can use this expansion as well. So in the numerator, imagine you have x minus x square by 2 plus x cube by 3 up till infinity divided by x. So this x cancels all these x. So in the numerator, you're left with 1 minus x by 2 plus x square by 3. So all these terms become 0 except for this one. And that's exactly what is written over here. Remember this as a result, the way we have learned x approaching 0, sin x upon x, tan x upon x, sin inverse x upon x, tan inverse x upon x were 1. Similarly, log 1 plus x upon x when x approaches 0 is also 1. These are some standard results which you are supposed to memorize. You should have these at your fingertips. The more well versed you are with these formulae, the chances are higher that you will be able to deal with the questions based on limits with more ease. That's exactly what I'm trying to point out here. Now, how do we solve questions based on this particular formula, based on this series? Of course, there is another series which is e to the power x. We have already discussed its expansion in the beginning as well when we were discussing the Taylor series. And yes, two more results come into picture, which are limit x approaches 0, e to the power x minus 1. Again, I hope you're realizing this one and this one is cancelled. So you're left with x square by 2 factorial, x cube by 3 factorial, and so on the numerator, and the denominator is x. This x cancels this x. So you're left with 1 only, along with a lot of terms in x. So when x approaches 0, you're left with 1. If you didn't understand this, the expansion method, apply L'Hopital. Why? Because when x approaches 0, this is 1 minus 1 upon 0, which is 0 by 0. So L'Hopital says e to the power x upon 1. X is approaching 0, so e to the power 0 will be 1. Through L'Hopital, you can find the answer to this formula as well, but I'll suggest that remember them as direct results. So the way we have learnt log 1 plus x upon x when x approaches 0 is 1. In the same fashion, don't forget that when x approaches 0, e to the power x minus 1 upon x is also 1. And a to the power x minus 1 upon x is log a at base e, ln a. Do remember it, right? Now, moving ahead towards the next set of rules or formulae or questions, what do we see next? Let's see if I ever get a 1 to the power infinity form. How do we deal with that? Instead of discussing this entire theory, I'll demonstrate it with an example. Although I'll tell you the direct formula, because at this stage, instead of giving you the entire proof, which I'm sharing in the notes only, this is the proof which you can remember. I'm giving the direct result. What is that direct result? Remember, let's say there is a function fx to the power gx. And when you apply limit x approaches a, and you see it as 1 to the power infinity form. What do I mean by 1 to the power infinity form? That when x approaches a, f of x approaches 1. When x approaches a, g of x approaches infinity. So whenever in a question, you see a question getting converted into 1 to the power infinity form, the general solution is, the standard solution is very simple. You write it as e raised to the power, the power of e. E should be the base. Limit x approaches a, f of x minus 1 into g of x. So you subtract 1 from it, and then to that you multiply it by gx. And this whole should be the power of e. So f of x minus 1 multiplied by g of x whole raised to the power e. That is the general solution. That is the direct answer. Do remember this as the direct conclusion. Instead of the entire derivation, which is very simple to work out, I am directly giving you this conclusion that whenever you have fx to the power gx, where x approaches a, this leads to 1 to the power infinity form, you can write that direct answer as e to the power, e should be the base, whole raised to the power, e should be raised to the power, fx minus 1 into gx, where x is approaching a. Did you get that result? If you are a little bit confused, I'll demonstrate it with an example. You'll get it completely. What is that example? Of course, before coming to that example, let me apply this scenario here in this case. Let me begin with this first case. I'll show some examples, but I'll give you some results and I'll prove these results with that previous result. Where? How? When x approaches 0, this is 1, this is infinity. So this is clearly 1 to the power infinity form. Now, how do we deal with 1 to the power infinity form? We deal with it as e to the power. We deal with it as e to the power limit x approaches 0, the base minus 1. So base is f of x, 1 plus x minus 1 is x into gx. What is gx? That is 1 by x. So x cancels x. So this is 1. Limit x approaches 0 and 1 is 1. So what are you left with? E. That's exactly what you are given over here. Did you understand it? I'll demonstrate it with this example as well. See, when x approaches infinity, this approaches 0, this approaches infinity. So 1 plus 0 to the power infinity, which means 1 to the power infinity. How do we deal with it? So the idea is very simple. E to the power, limit x approaches infinity, f of x minus 1. So 1 plus 1 by x minus 1 will be 1 by x into g of x. What is g of x? X. Again, this x and this x are cancelled. And again, you are left with e to the power 1, which is e. So are you understanding how am I using this result 1 to the power infinity form? Let's apply it here. Again, when x approaches 0, this is 0, this is infinity. So this is 1 to the power infinity. How do we deal with that? Answer should be the direct answer I'm trying to tell you here. Don't learn anything. At this stage, learn this short technique and apply it in all the questions. The answer is e to the power limit x approaches 0, f of x minus 1. So 1 plus lambda x minus 1 will give you lambda x into g of x. What is g of x? Sir, 1 by x. So this x and this x are cancelled. You are left with lambda. Lambda is not affected by x approaching 0. So this is going to be e to the power lambda. Did you get that result? I'll demonstrate it with this example as well so that you completely and comprehensively get this part very clearly. See, x is approaching infinity. So lambda upon infinity is 0. This is infinity. So 1 to the power infinity. How do you deal with this? Answer will be e raised to the power limit x approaches infinity, f of x minus 1. So 1 plus lambda by x minus 1 will be 1 cancelled. You're left with lambda by x into g of x. What is g of x? That is x. X and x are cancelled. You're left with e to the power lambda. That's exactly is the correct answer. Did you understand this short technique? This is indeed a short technique, but rather this is a formula actually. I am asking you to remember these results as well. I am very clearly and constantly asking you to remember these 4 results as well. Even if you forget these 4 results, do you have that standard formula in your mind? The formula which we have just discussed, this one. Do remember it. It is again a very crucial one, which we will be using at a lot of places. The moment you see 1 to the power infinity, don't hesitate in applying it. Just apply it and get the answer. You will get the answer within moments if you remember this formula. But this is applicable only when you have 1 to the power infinity form. Do you get that? Of course, we will be dealing with 0 to the power 0, infinity to the power infinity, other forms as well. But as of now, this is the standard formula for 1 to the power infinity form. How do we apply it? Let's look at this question asked by JEE Mains in 2025. And then we'll explore that how do you apply 1 to the power infinity formula in this category of questions. Look at that. Here. Sir, first of all, it is the primary job of ours to identify what kind of form it is. Yes. So what I'll do is, I'll begin with this part that e by 1 minus e and this 1 by e minus this. So let me simplify this expression first and then I'll multiply it here. Okay. I am trying to work on denominator first, then I'll look at this. Because when you see this power becoming infinity, this will be either 1, 0 or infinity. So let me see what does it approach to. Okay. So here, let me simplify this. The base basically. So it is e by 1 minus e. I'm looking at the base only. Okay. Now multiplied by 1 by e minus x upon 1 plus x. I hope there is no confusion on that. I'm looking at the base only. Now, if I take the LCM here, it is going to be, I'll write it directly here as 1 plus x minus ex divided by e times 1 plus x. Did you get that part? I hope there is no confusion on that. I'm writing the base right now. Okay. Now, when you multiply this part with this, so I think this e and this e are cancelled. In the numerator, it is 1 plus x minus ex. So if I take x common, I'm left with 1 minus e whole times x plus 1. I hope you are noticing it very clearly. And in the denominator, this 1 minus e, when I multiply it with 1, it will be 1 minus e. And when I multiply this 1 minus e with this x, it is 1 minus e times x plus of course 1 minus e. So this is how the simplified version of our denominator looks like. Sorry, the base looks like. So this is the simplified version of our base. Although it was raised to a power x, so this was raised to a power x. Let me write that power as well. And here limit x approaching infinity was given to me. So this was limit x approaching infinity. Now what I'm trying to make you understand is that here, when you notice it here, numerator and denominator both are polynomial in degree 1. So they are linear expression and x is approaching infinity. So we know that if numerator and denominator have the same degree, if they are of the same degree, in that case, we say that the coefficients of x, the ratio of the coefficients of x will be the answer. So if I simply look at this expression only, if I forget this x for a while, so this base is giving me the answer 1 minus e upon 1 minus e, which is 1. So are you not noticing that this base is approaching 1, where this power is approaching infinity, which means this is clearly a 1 to the power infinity form? Have you understood this particular part? Now, the moment we crack that this is a 1 to the power infinity form, we know the logic. The answer as per our understanding, as per our logic, will be simply e raised to the power f of x. F of x is our base minus 1. So I'll be subtracting 1 from this. I'll be subtracting 1 from this. What is it? It is 1 minus e times x. Okay, so it is 1 minus e times whole of x plus, what do I have here? Plus 1, right? Plus 1 whole divided by 1 minus e times x plus 1 minus e. So this is 1 minus e times x plus 1 minus e. Let me just check it. 1 minus e times x plus 1 minus e. And 1 minus e times x plus 1 is the numerator. This is f of x. So f of x minus 1 is what we do in the numerator, multiplied by g of x. What is g of x, students? I hope you remember g of x is the power, which is x. Do you remember this as a general solution? And of course, this entire expression is raised to the power e, where limit x approaches infinity is needed to be applied. So that will be our answer. But of course, this needs to be simplified, which I'll do later. But are you understanding how are we working upon this? This expression was found to be of 1 to the power infinity form. So what is the standard technique here? E to the power f of x minus 1 gx. This expression should be applied with this limit x approaches infinity. Did you get that part? I hope there is no confusion. Now I'll be simplifying it further. So what do we get next? So my next result will be e to the power, right? Of course, limit x is approaching infinity. Now let's look at this power. If I were to simplify this, what result do I get? So see, what I'm seeing here is that 1 plus e times x plus 1. So I'll write it very clearly, although a lot of you can predict the conclusion, but still if you get confused, if you are prone to committing any silly mistake or error, I'm writing it completely. So I'm taking the LCM here. So this plus 1. This I'm multiplying with this minus 1. So this is minus 1 minus e times whole of x minus whole of 1 minus e whole divided by 1 minus e times whole of x plus 1 minus e, right? I hope there is no confusion on that, divided or multiplied by x. Did you get that part? All I have done is 1 minus e x plus 1 minus this, then minus of this divided by this in the denominator into x. I'm just verifying it so that we don't commit any error. Now, look at this part. How do I proceed further? Are you not noticing that, sir, 1 plus e whole times x, 1 plus e whole times x is nullified? Not just that, this one cancels this one. So in the numerator, we are left with plus e. Why am I saying plus e? Because of minus e will be plus e. Did you get that part? I hope there is no confusion on that. So it gives me e to the power limit x approaches infinity, and the numerator has plus e in the numerator, divided by, of course, the numerator has this x as well, and the denominator has 1 minus e times x plus 1 minus e. Now, are you not noticing the same logic can be applied again, which we have applied in finding out the base to be 1? Why and how? See, x is approaching infinity. So this is an infinity by infinity form. You can apply L'Hopital as well. Or rather, I'll say, if both of the numerator and denominator have degree 1, same degree polynomials, which means the ratio of their coefficients of highest degree term will be the answer. So answer should be e upon 1 minus e. I repeat, x has a coefficient e here. This x has a coefficient 1 minus e. So the answer will be e raised to the power e upon 1 minus e. So my answer will be e raised to the power e upon 1 minus e. But that is not the answer to the question. This is the value of alpha. Now I need to find this. Okay, so I think we have cracked alpha. we have cracked alpha, and alpha is found to be as e raised to the power e by 1 minus e. That is the conclusion we have received as the value of alpha. Yes, e by 1 minus e. Now, we need to find this. Okay, so can you help me with ln alpha? So if I am taking log on both the sides at base a, at base e, it should be this e, log e base e will be 1. So I'll be left with e by 1 minus e. So I hope first of all ln alpha will be e by 1 minus e. Did you get that? So I'll replace these values here. E by 1 minus e, 1 plus this e by 1 minus e. That is what we are asked. So I hope the answer is pretty simple. So log alpha, ln alpha at base e will be e by 1 minus e divided by 1 plus, I hope it is 1 plus ln alpha, which is again e by 1 minus e. I hope it's simple and easy to figure out the answer now. It's very simple and straightforward now, because in the numerator it is e by 1 minus e, in the denominator it is 1 minus e plus e, right? So in the denominator it is 1 minus e plus e. Did you get that? It is 1 minus e plus e. And then the numerator it is e, because 1 minus e and 1 minus e as LCM are cancelled and nullified. I hope you all are realizing the final answer will be e, because this e and this e are cancelled and you're left with e only, because 1 minus e plus e is 1, and then the numerator you're left with e, and that's your answer, which is given in option D. Did you understand the whole process? Did you understand the whole question? More importantly, were you able to understand that how are we seeing it as 1 to the power infinity form and how are we cracking it? Always remember, whenever you apply a limit should be applied on the entire expression. You cannot apply it partially. That, sir, I'm applying the limit here and then I'll apply it here later. No, you cannot do it. So whenever you solve questions based on limits, apply the entire limit on the entire expression. You cannot apply it partially. Do remember this as a fact. Now, moving ahead towards the next set of rules which we'll be discussing. Yes. How do we deal with 0 to the power 0 form? So whether you deal with 0 to the power 0 form, infinity to the power infinity form, infinity to the power 0 form, these kind of indeterminate forms always take logarithm on both sides. I repeat, even whenever we were dealing with 1 to the power infinity form, the derivation of that formula, that short technique which we have discussed, was based on this only, that you take logarithm on both sides. So when you take logarithm on both sides, then it can be converted into either 0 by 0 or infinity by infinity form through some adjustments. I repeat, whenever you see 0 by 0 form or something like other forms as well, 0 by 0 form, infinity to the power 0 form or something like that, always take logarithm on both sides. I'll prove how and I'll show how. Look at this particular question. This is a question again, where if you try solve it, asked by JEE Mains in 2025, an interesting one, through which I'm just trying to give you the idea that whatever this power of indeterminate form comes, 0 by 0, infinity to the power 0, 0 to the power infinity, infinity to the power infinity, if you deal with such forms, then always remember, taking logarithm on both sides is always advised. But don't forget, what usually students do is, in a rush, they mark the answer as the value of logarithm. They forget to take NT-log in the end. So don't forget that you are supposed to take NT-log as well. I repeat, don't forget that you need to take NT-log as well. I'll tell you why and how. See, look at this particular question. This says limit x approaches 0, this to the power this. I hope most of you must have already seen and understood, sir. 10x upon x, when x approaches 0 is 1. We have discussed this standard result. And 1 by x square is basically what? Infinity. So this is 1 to the power infinity form. So how do we deal with it? I hope I need not tell you. You have the short technique. And even if you forget the short technique, you can take logarithm and solve it. So we have both the methods. I think we can apply the short technique directly. So how do we apply the short technique here? I repeat, you can use logarithm method as well, which is nothing but that short technique directly. So can we use that short technique directly? So how do I write this answer here? I'll have answer as e to the power. The answer or the expansion of the value of p will be e to the power f of x. So limit x approaches is 0 there. Why am I doing all this? Because this is clearly 1 to the power infinity form. And the moment you see 1 to the power infinity form, you can directly apply this short technique, the formula. It is not actually a short, there is nothing as short technique. This is simply a terminology which we use to fool you, the students' fraternity. But actually they are all formula, they are standard methods, they are derived results. So we are using these derived results and we are calling them short techniques, right? But of course, they help you a lot. They end up saving a lot of time of yours. So that's where you call them short techniques, right? So here I'll say that here it is getting converted into 1 to the power infinity form. And if it is called a 1 to the power infinity form, there is a formula. What is that? E to the power, the same limit, fx minus 1. What is fx? Sir, fx is 10x by x minus 1 will be this times g of x. What is g of x? Sir, it is 1 by x square. Did you get that part? I hope there is no confusion on that front. Now, if you remember the expansion of 10x, and if you have forgotten it, I'll show it to you one more time. I hope you must have seen those results which we have discussed in the expansion of 10x here. I'll just show you here. There we have it. I think here it was. I hope you remember. 10x is also an odd function, so you'll have odd powers of x, x cube, x to the power 5, x to the power 7, and so on. They'll all values will be plus with plus sign. But here what you need to remember is the coefficient are 1, 1 by 3, 2 by 15, and so on. I hope you'll remember it. So 1, 1 by 3, 2 by 15, and so on. Right? So where were we? We were, I think, here. Where were we? Yes. Now, look at this part. I am writing the expansion of 10x. So what is it going to be? It is here, x approaching 0. Now, I'm writing the expansion of 10x. I hope there is no confusion on it. Here, first of all, right before writing the expansion of 10x, can I say it will be 10x minus x upon x, and that x into x will give me x cube. Now I'm writing the expansion of 10x at this stage. How will it look like? See, the expansion of 10x, right? e to the power limit x approaches 0 whole raised to the power what? 10x, we know 10x is x, then plus power 1, then power 3, x cube. So 1 by 3 is the coefficient, then plus x to the power 5. What is the coefficient? 2 by 15, x to the power 5, and then so on, right? Higher powers of x, x to the power 7, x to the power 9, and so on. So this is the expansion of 10x, right? From this, I'm supposed to subtract x. Okay, I'll subtract x from here. So I'm subtracting x from here. And this is needed to be divided by x cube. Do you remember this conclusion? I hope there is no confusion on that. A great clarity you are able to generate based on this. This entire is raised as a power of e. Now, what do you understand by this expression? This x and this x are cancelled. Do you all agree with this? One more thing you all can do, which you can, through which you can actually skip one more step. Avoid writing one more step by doing this, that this x cubes cancel this x cube, x to the power 5, and a lot more steps. So if you do that, this x cube nullifies this x cube. So there you are left with 1 by 3 plus you are left with 2 by 15 x square and some higher powers of x, right? And there you are left with limit x approaches 0, this entire expression as the power of e. I hope you all are realizing that this x approaches 0, all these terms will become 0 and you're left with 1 by 3. So your answer will be e to the power 1 by 3. That's the value of p. That's the value of p. Although in this question, they have already asked you 96 times log p base e. So if p is e to the power 1 by 3, let me just verify it one more time. P is e to the power 1 by 3. I hope you know what is going to be the value of ln p. So ln p, I hope you are realizing, will be 1 by 3. Did you get that part? I hope you know how to take logarithm. So log of p at base e will be 1 by 3. I hope you remember it. Now, we are not asked ln p at base e, we are asked 96 times of it. So 96 times log p at base e will be 96 by 3, which I think will be 32. And that's your answer to this question. I hope there is no doubt, confusion, or hesitation on that. You are able to get a lot of sense, a lot of clarity on this front now. How do you deal with questions based on 1 to the power infinity, 0 to the power 0, infinity to the power infinity, infinity to the power 0, something like that, by taking logarithm on both sides. But in the end, don't forget taking the anti-log. Although in this question, they have asked you question on logarithm as well. Log of that value only. So even if I forget taking it, I am very close to that answer only. But still, make it a habit that whenever you solve questions by taking log on both sides, in the end, remember to take anti-log. In a rush, students do write the value with logarithm, and that's where they end up getting the incorrect marks, negative marks. So remember that once you have put your entire efforts in solving a particular question, why should you not have the correct or the right amount of marks? Well, that can be achieved when you take care of such nuances, such minute details, where if you're solving a question by taking logarithm, please take anti-log in the end. I hope you'll remember it. Now, moving ahead with the next set of rules, what do we have next here? Let's explore the further part. We are now going to discuss left-hand limit and right-hand limit, as we have already discussed it. I think I need not explain this part. In the beginning of the conceptual understanding the concept limits, we have had a discussion on this particular part. Look at this particular question. This will give you a complete, greater, better clarity on the concept of limits. Rather, the left hand and the right hand limit. How? See, it says 0 should be approached, but from right hand side only. And that is a valid reason here in this question, because when you deal with under root x, you cannot approach 0 from left hand side in that expression, because when you approach 0 from left hand side, it will be taking negative values. And can x take negative values? No. Under root x cannot have x negative values, because when you replace x by negative values, under root x will be not defined, and that's where this limit will not exist. So that's where they're not saying that x is approaching 0. If they say that x is approaching 0, then whatever you get the value of this expression when x approaches 0 from right hand side, and the value which you will solve by getting x when x is approaching 0 from left hand side will be different. Why will it be different? Because when x approaches 0 from right hand side will be different, but when x approaches 0 from left hand side, it will go not defined, and when it is not defined, the limit wouldn't exist. And in that case, you will say that the limits LHL and RHL are not equal. And if the left hand limit and the right hand limit are not equal, then you will say that limit does not exist. Then you say that the limit does not exist. Do you remember that? But here what you need to understand is very clearly they have avoided that problem here. They have very clearly avoided that problem, that contradiction, that x is approaching 0 from right hand side only. So you need not bother about its left hand limit and right hand limit, and then you find out both, and then they should be same. And once they are same, then you say that the limit x approaches 0 will be this. No, you need not do all this. Whenever there is this delusion, this dilemma, this problem, or this error or contradiction, you need to deal with both the limits. Whenever you see that left hand limit could be something else, right hand limit could be something else, you should be more clear with that. For example, here, look at this graph. Let me draw the graph of, let's say, fraction part function. So the graph of fraction part function is drawn like this. Now let me try and help you with this result. Let's say at this point, this is 1, this is 0, this is 2, of course. Of course, we all know this is 1. So we know that the fraction part function attains all the values from 0 and 1 only. If I am approaching 1 from left hand side, it is approaching 1. But if I'm approaching 1 from right hand side, it is approaching 0. So I hope you're realizing when you talk about the limit when x is approaching 1 on fraction part of x, then you will say the limit doesn't exist. Why did I say so? I said so because the left hand limit and the right hand limit were not same. I hope you're realizing when I apply limit x approaching 1 from left hand side. When I approached 1 from left hand side, the graph was approaching 1. I hope you can see it very clearly. So fraction part of x when x approaches 1 from left hand side was 1. So left hand limit exists. That is perfectly fine. When I apply x approaching 1 from right hand side on this function fraction part of x, what does it say? Sir, x is approaching 1 from right hand side. So the graph is approaching 0. I hope you can see it here. Even the right hand limit exists. That is 0. Both exist, but both are finite, but both are not same. And if both of them are not same, in that case, I'll say that the limit x approaches 1 of fraction part of x doesn't exist. So functions like fraction part of x or GIF of x, they become discontinuous because they are having their limits not same, the left hand limit and the right limit at integral values of x. I hope you can see this clearly happening over here. So that's the point I'm trying to make you understand. When you look at these piecewise functions, they create trouble, they create problems with their left hand limit and right hand limit, and that's where you need to be more clear with such expressions. For example, under root x. So this under root x for x approaching 0 from left hand side will be not defined, and that's a problem here. So we'll be seeing it from 0 plus only, and that's what they have already given you in this question only. So let's solve it now from that perspective. We'll be using a lot of things here, but let me first of all write this expression. So we are dealing with 10 of 5 times x to the power 1 by 3. Okay. Then I am having another expression which is log of ln of basically 1 plus 3x square. All right, that's great. Whole divided by this expression. This entire expression is divided by 10 inverse of 3 root x square, right? And then what is next? The next expression is e to the power 5 times x to the power 4 by 3 minus 1. All right, that's great. That's great. And we are told that x is approaching 0 from right hand side. Brilliant. This is what we are dealing with. Even if I wish to write it here, I can write this x as x to the power 1 by 2. So I'm writing it as 3 x to the power 1 by 2. I hope you are comfortable with this. Do you remember some standard results? What do I mean by some standard results? Do you remember 10x upon x approaches 1? Why should we not use it here? So 10 of something upon that something with something 5x to the power 1 by 3. Now, if I have divided this by this, I should multiply it by it so that the equation remains balanced. So I'm multiplying it by 5x to the power 1 by 3. Similarly here, log 1 plus x upon x when x approaches 0 is 1. So if this is x, which is 3x square, I am having a 3x square in the denominator. And if I'm multiplying it, dividing it by 3x square, why should I not multiply it to keep it balanced? So here I'll have another 3x square in the numerator. Did you understand this whole front? Now let's look at this part. Do you not remember 10 inverse of x upon x is also 1 when x approaches 0? So 10 inverse of this, which is 3x to the power 1 by 2. If I have multiplied it by divided it by this, I should multiply it by this, but this is squared. So if I'm writing it outside this bracket, I need to write it's a square. So 3 square is 9 and x to the power 1 by 2 when squared gives you x. Are you comfortable with that? Now here, we have discussed one more result. E to the power x minus 1 upon x also approaches 1. And there you should remember that here it is 5x to the power 4 by 3. So I'm dividing it by 5x to the power 4 by 3. So I should multiply it by 5 times x to the power 4 by 3. I hope there is no confusion on that. Now, the advantage of x approaching 0 from right hand side is pretty simple. This wouldn't create any problem. This wouldn't create any problem. This wouldn't create any problem. The only problem was with under root x. Had it been x approaching 0, I would have to take the left hand limit and right hand limit separately, and then I'll have to evaluate both of them, and then I'll commit that if both of them are not same, the left hand limit and the right hand limit, then the limit doesn't exist. But here in this case, I need not bother about the left hand limit and the right hand limit because they have specifically asked about the right hand limit. And that's where I need not bother because under root x is defined for the positive values of x. So very small values of x are given 0.1, 0.2, 0.3, but still they are positive and their square root can be taken. I hope you're understanding the intent. So if on this x approaching 0 plus is applied, they still approach 1, which I hope you remember 10x upon x. So if this is 5x to the power 1 by 3, this is 5x to the power 1 by 3. So 10 0 upon 0 because this is approaching 0, this is also approaching 0. So this entire expression is approaching 1. Log of 1 plus x upon x. I hope you're realizing x is approaching 0, 3x square basically. So log of 1 plus x upon x is also approaching 1 when x approaches 0. Do you remember that? 10 inverse x upon x. This also approaches 1 when x approaches 0. E to the power x minus 1 upon x also approaches 1 when x approaches 0. So I have gotten a great result. But while doing it, I have made some errors. Let me check what I have done with this question. I have introduced some more terminologies. I have introduced some more terms here. Are you not noticing them? So why am I not applying the same limit there on those terms as well? Let me try and look for what I have done here. Let me try and look for what I have done here. See, the numerator has 5x to the power 1 by 3. The numerator has 5x to the power 1 by 3 times 3x square. Okay, so that is 3x square. As we have discussed, when you apply limit should be applied on the entire expression. So I'm trying to work on this remaining rest of the expression as well. What does it become? This is 9x and that is 5x to the power 4 by 3. So this is 9x and that is 5x to the power 4 by 3. Let me just cross check it again. 5x to the power 4 by 3. Great. Now, what I'm trying to make you understand is, let me see what is happening with this expression because that limit should be applied on the entire expression. So let me simplify. What do I get from here? Okay. Now, what I'm seeing is x to the power 1 by 3 x square. So I'm seeing x to the power 1 by 3 plus 2 here, and here x to the power 1 plus 4 by 3. What is happening with these coefficients? 3, 3, that is 3, 5, 5. So this is 1 by 3, right? So this is 6 plus 1, 7. This is 3 plus 4, 7. So this is x to the power 7 by 3 divided by 3 times x to the power 7 by 3. So effectively it is, I hope you're realizing 7 by 3 are cancelled. You're left with 1 by 3 only. So are you not noticing that this into this upon this into this is 1 by 3 only? So when I apply limit x approaches 0, no 0 is affecting this part here. because this into this upon this into this is leaving us with 1 by 3 only. So that 1 by 3 into 1 into 1 into 1 into 1 will be 1 by 3. Did you get that part? Did you get that part? I hope there is no confusion on that. So my final answer to this question will be 1 by 3. I hope there is no confusion on that and you have gotten a great clarity on this, that how have we cracked this particular question. Are you able to make some sense out of it, that how should we use these results, the results which were given to you, log 1 plus x upon x, tan inverse x upon x, tan x upon x, e to the power x minus 1 upon x. When x approaches 0, they all lead to 1. They all approach 1. That's exactly what I have utilized here. Did you get this part very clearly? Now, if you have understood this front, let me move ahead towards the next part where we'll be discussing the next topic, which is sandwich or squeeze theorem. It simply says that, let's say, if there are two functions, let's say one of the functions is this, fx, right? This is, let's say, hx, and there is another function which is fx. And at a certain point, let's say hx and fx become almost equal, right? And there is another function which is gx. And we know that gx is always greater than fx and it is always less than hx. What I'm trying to say is that we know that fx is less than gx and gx is less than hx. We know this is true for all x in its domain if we are seeing the function now. Yes, in some interval, let's say I'm saying, and then at certain point, let's say at 0, what we notice is that when f of x, let's say at 0 or c, at whichever point, let's say c, at 0, let's say I'm seeing that f of x and h of x are approaching same value. Let's say in this case, that is 1. Let's say they are approaching the same value, which is 1. So by sandwich theorem, by squeeze theorem, you can say that even gx will also approach that one only. Because see, all the three functions are continuous. I'm giving you an analytical proof of this expression. hx is going from here, fx is going from here, gx is bound to pass between them. So at a certain point, hx and fx have come so closer that there is no space between them. So from where will gx pass? Gx has to pass from that point only. So if I could not determine the limit of gx at that point, I will determine the limit of hx and fx at those points. And if that is turning out to be same, which means gx will also pass through that narrow passage only, which will be same as hx and gx at that point. Are you getting that part? So always remember, gx will also approach the same value L if fx and hx are approaching a value L at c, when x is approaching c. Because if hx and fx are clubbed together like this, they have created no space here, then gx is also bound to pass through this passage only, because this is the inequality which you need to ensure, that f of x is less than g of x and it is less than h of x. So g of x will lie between them only. Are you getting it? So gx will approach that value L only when x approaches c, because fx and hx are also approaching that same value. They are squeezing it. They are making a sandwich out of it. Did you understand this theorem? It is used especially in those questions when we cannot find the limit of g of x directly. Then we find two functions such that those two functions sandwich this function. I repeat, if I could find two functions for gx, for example, fx and hx, in such a manner that fx is less than gx and gx is less than h of x for some interval, and in that interval we find a value c. At that value c, we are trying to find its limit, and we cannot find its limit directly. Then we find the limits of h of x and f of x at c, and let's say they are found to be same, they are found to be equal. In that say, we conclude that g of x will also have the same limit at that point. Why? Because it is bound to pass through that narrow passage only. Are you understanding this squeeze theorem, the sandwich theorem, very clearly? I hope it makes complete sense. It makes great sense. Now, let me talk about one more result, which is this, that here, this is something which we have already discussed, limits of trigonometric functions. This is a very crucial result which you should take care of. Keep this result in mind. Students commit an error here. We know sin x upon x when x approaches 0 is 1. That is perfectly fine. But you should remember, there is a very crucial result, that sin x upon x approaches 1 from left hand side. That is, it becomes 0.998, 0.999 and so on. So whenever somebody says that you need to find limit x approaches 0, GIF of sin x upon x, then the GIF of these values is needed to be taken. This sin x upon x approaches 1, but from left hand side. So 998, 0.999, 0.9992, something like that keeps on happening. So when you take the GIF of these values, the left hand side values of 1, they become 0. So if somebody asks you limit x approaches 0, GIF of sin x upon x, it wouldn't be 1. Because you won't say that sin x upon x will be 1, then its GIF will also be 1. No, it is the approximation, it is the trend, it is the pattern towards it is approaching. So sin x upon x approaches 1 from left hand side, 0.99, 0.98, 0.97. And when you take the GIF of it, it results into 0. Similarly, when you talk about 10x upon x, this is also 1 when x approaches 0. But it approaches 1 from right hand side. For example, 1.1, 1.2, 1.3. When you take the GIF of it, it becomes 1. Please don't forget it. Remember it as a result. I am asking you to take a screenshot of this particular slide. Do remember this as a result. This is something very crucial. They ask tricky questions on that and students end up committing errors on this particular front. So do remember this particular result. Okay. I hope you won't forget that. Now, moving ahead towards the next set of results here. This is a Newton-Leibniz formula. I'm skipping this at this stage because this formula I'll be discussing in definite integration. When we discuss the chapter definite integration, there will be discussing it. So instead of giving you a clarity here, I'll simply put it into the notes. When you receive the notes, when you receive the PDFs, you will have these notes in this concept in these notes here as well, and definite integration as well. But with apt illustrations and example, I'll discuss this Newton-Leibniz formula there in definite integration. So don't worry, we'll be discussing it there. I'm skipping it in this limit part because so far, let's say we don't know definite integration. So how will you be able to do it? So let's assume that we will understand integration only after understanding integration. So after indefinite integration, we'll study definite integration. There, I'll tell you that there were certain questions based on limits, which can be done with the help of sandwich formula as well, and they can be generalized into this limit as a sum as well. This formula, Newton-Leibniz formula, that is what we'll discuss. I'm really sorry, limit as a sum is something different. Limit as a sum can be done with sandwich theorem, which is what we'll discuss now. But before that, I am trying to give you this idea that Newton-Leibniz formula, where you are asked to deal with certain questions, where you are differentiating a definite integration, there is a standard technique for it given by Newton-Leibniz, which is what will be discussed under the chapter definite integration with appropriate examples. So I'm skipping this at this stage. I'm simply moving towards this part, summation of series using definite integration. This is something I'd like to tell you here at this stage only. Now, what is it? I'll explain it with an example only. See, this question can be done with sandwich theorem, squeeze theorem as well, but I'd like to tell you that this category of questions can be done with this limit as a sum as well. How? Let me try and tell you that. First of all, try to generalize its term. What do I mean by that? This is summation, where n is approaching infinity. So that is the limit. So limit based question it is. But there I'm seeing it as a generalized sum. What do I mean by that? This is this expression when I'm writing it as 1 by n to the power p plus 1. Can I write this 1 by n out of it? So this is leaving me with n to the power p only. From n to the power p plus 1 in the denominator, I'm taking 1 n common. So I'm left with n to the power p. So what am I now left with? 1 to the power p divided by n to the power p plus 2 to the power p divided by n to the power p and so on, right? Even if I wish to generalize it, can I not write it as 1 by n to the power p plus 2 by n whole raised to the power p plus and so on 3 by n whole raised to the power p up till n by n whole raised to the power p. But here what you need to understand is that this n is approaching infinity. Great. So this is an expression. This question can be done with the help of limits. This question can be done with the help of squeeze theorem, sandwich theorem. But I am giving you another method where you use the concept of limit as a sum. How? Let's have a look at that part. Now, if I could generalize this expression, I'll be able to crack this question within 2 seconds. What is that method? That method is what I'm trying to tell you through this illustration, through this example. Instead of giving you the theoretical explanation, I'm giving you an illustration through which I'll be demonstrating you how should you use this particular concept. So this limit n approaches infinity stays there. You don't touch it. This 1 by n stays there. If I were to generalize, the first term has 1, second term has 2, third term has 3, nth term has n. So this is basically a question on summation. This is basically a question on summation of an expression r by n whole raised to the power p, where r has started with 1 and it is reaching till n. Did you get this part? 1 by n, 2 by n, 3 by n, which can be written as r by n raised to the power p. And here r is starting with 1 and it is reaching till n. Did you get this part? Did you understand this part? This is something which you should be able to create. So whenever summation based questions are there, if you generalize a pattern here, then this kind of conversion you should be able to make. Why? Now I'll answer why. Because I'll use some transformations. I'm sharing another technique with you, a direct technique. So the changes which you do is, always remember, we replace r by n by x. This is the technique. This is the idea. This is the hint. This is the formula. This is the trick. Trick is a very bad word here. I'll say the standard technique. So r by n is replaced by x. That summation sign gets converted into the sign of integration. This 1 by n is replaced by dx. Now you put the lower limit and upper limit on this integration. So let's say there is a lower limit and the upper limit. To find lower limit, see, this r is 1. So in r by n, you replace 1 by n and you make limit n approaches infinity. So 1 by n is going to be 0. So this 0 is going to be the lower limit. So what about the upper limit? See, when you talk about the upper limit, you say limit n approaches infinity. R started with 1. R has approached n. So this is going to be n by n. So in r by n, initially I replaced r by 1 for the lower limit. Now I initially replaced r by 1 in the lower limit. Now I'll replace r by n for the upper limit. So it is going to be n by n. It is going to be n by n. So n by n is 1. When n approaches infinity, 1 is going to be 1. So that is going to be the upper limit of that definite integration. This expression, which is given in the form of summation, can be written as an expression of, of course, this limit n approaches infinity 1 by n, this entire expression can be written as dx, right? Now, or you can put it anywhere, basically it gets vanished. So this is what you're left with. What I am trying to tell you now again, please pay your complete attention here at this front. Now, this is something very useful. This summation with this limit gets converted into the sign of integration. Great. What about the lower limit and upper limit? The lower limit is 0, the upper limit is 1. So lower limit will be 0, upper limit will be 1. What about the next part? Sir, this 1 by n should be treated as dx, so I'm writing it as dx. Then what am I now left with? I'm left with r by n to the power p. But r by n should be replaced by x. So my answer now becomes x to the power p. That's the final stage which we have attained by converting that question based on limit into a question of definite integration. Along with this, what you also should understand here at this stage is that here one more thing is there, that if I wish to integrate x to the power p, p is an arbitrary constant, so we know that integration is going to be x to the power p divided by p plus 1. Sorry, it should be x to the power p plus 1 divided by p plus 1. I hope you remember that. There is no confusion on that. And of course, the limits are going to be 0 and 1. Do you remember that? I hope there is no confusion on that. I hope you are understanding it very clearly. Now, when I solve it further, what result do I get? I hope you know how to pass on these limits. So the limits are going to make it 1 to the power p plus 1 will be 1 divided by p plus 1. And when you replace 0 here, this is 0 to the power anything by 0 will be 0 to the power anything by something constant will be 0. So the final answer is 1 upon p plus 1. Did you get that result? Did you understand it? Were you able to make complete sense out of it? I'll make you revise this part again where you should not get confused. And this is something very crucial and very important. IIT JEE loves it. I have taken a very simple example through which I have tried explaining this to you. Let me try covering the important parts highlighted one more time. Let me try highlighting this again. See, we started with this summation. What we did was 1 by n to the power p, 2 by n to the power p, 3 by n to the power p, up till n by n to the power p. So this is how I could generalize it. Even more general form of it will be 1 by n and limit n approaches infinity was there. This can be written as summation r by n whole raised to the power p, where r is starting with 1 and it is reaching till n. Now the moment you see this, the moment you see something like this, when you see something like this, This is what you should have. This is what you should have. This is what you must remember. What is that result? Let me talk about that result. That result says that limit n approaches infinity with this summation sign should be replaced by integration. Limit n approaches infinity basically vanishes. Whether you club it with this or this, that doesn't matter. But you should understand that this becomes the sign of integration. This 1 by n becomes dx. R by n becomes x. Now, when it comes to writing the lower limit and the upper limit, because it is something definite, then you say that in R by n, put this initial value. So it is 1 by n, and 1 by n when n approaches infinity will be 0. That is your lower limit. Put this here, put this n here in place of r, that will be n by n. So n by n when n approaches infinity will be your upper limit, which is 1. And this expression can now be converted into this expression. 0 to 1 limits, integration dx, r by n become x, so x to the power p. And we know how to integrate x to the power p because p is an arbitrary constant. So p to the power x to the power p plus 1 upon p plus 1, 0 to 1 is limit. Answer will be 1 upon p plus 1. That is what you are given in option A. Did you understand this completely? Did you get a great clarity on the concepts of limits? I hope we are comfortably understanding how should you solve questions based on this particular concept. Now we'll be talking about continuity and then we'll gradually move towards the concept of differentiability. Right. So let's start with the concept of continuity now. Okay. Continuity is a very simple concept. In a layman's language, I'll say that while drawing the graph of a function, if you don't have to lift up the pen, while drawing the graph of the function, if you don't lift up the pen, you can draw it continuously without the graph gets broken. If the graph is not broken, then you'll say that the function is continuous. Did you get that part? For example, let's say if you look at the graph of sine x. So if I draw the graph of sine x, how will you draw it? It's a very standard, straightforward graph, and without any confusion, you would say, sir, sine x graph, we can draw like this and it keeps on going. So if this graph keeps on going and it does not break, then we say that sine x is a continuous function. But what if I draw the graph of 10x? Now, if I draw the graph of 10x, look at the graph of 10x. Of course, 10x from minus pi by 2 to pi by 2 goes like this. But from pi by 2 to 3 pi by 2, it goes again like this. But at this point pi by 2, it is not defined. The graph breaks. It was going like this, then it got continued from like this. So between minus pi by 2 to pi by 2, it is continuous. But from 0 to pi, I'll say it is discontinuous at pi by 2 because the graph broke. I hope you are understanding the basic standard meaning of continuity. Now, how does limit help in deciding the continuity of a function? That is what we'll be deciding at this stage. I'll demonstrate different cases, different scenarios, different examples, and I'll just try and make you understand the different cases. For example, look at this part. At x is equals to a, the left hand limit, the right hand limit, and the value of the function, all three of them were same. So whenever the LHL, the left hand limit, the RHL, which is the right hand limit, and the value of the function, which is f of a, if all three of them are same, then we say that the function is continuous. I'll demonstrate it. Look at this part. Here, this is left hand limit. So left hand limit is this. This is right hand limit is this. Even the value of the function is this. So in this case, the value of the function and the right hand limit are same, but it is not equal to the left hand limit. And if it is not equal to the left hand limit, if all three of them, the left hand limit, the value of the function, and the right hand limit, if all three of them are not same, then we say that the function is discontinuous. I'll share some more examples and scenarios. For example, look at this scenario. Here, you must notice the left hand limit and the value of the function is same, but it is not equal to the right hand limit. And there we see a gap here. That is how the function is getting discontinuous. Look at this part. The left hand limit is leading to me here. The right hand limit is also leading to me here. So in this case, the left hand limit and the right hand limit both are same. The left hand limit and right hand limit both are same. But look at this. At a, the value of the function is same, not the same. So LHL and RHL were same. They were taking me towards the same point, but at a, the value of the function was different. And again, if all three of them are not same, I'll say that the function is discontinuous. Because see, the graph went like this, it broke here, and it went like this. So it is discontinuous at a. Are you not noticing it? I'll show some more functions, some more scenarios, some more examples. Look at this. I hope you are noticing left hand limit, right hand limit, but the value of the function is different. LHL, RHL functions value, both, all three of them are not same, hence it is discontinuous. Look at another classical case. At a, it is not defined. At a, the function is not defined. From left hand side, it is approaching infinity. From right hand side, it is approaching infinity. So LHL and RHL are not finite, they are infinite, but still they are approaching infinity, but still at A it is not defined. And again, I'll say it is discontinuous. Are you understanding the different scenarios, the different cases I'm trying to give you here? So basically, discontinuity, I hope you are able to understand and digest that in order to make a function continuous, you need to ensure three things: the LHL, the RHL, and the value of the function. If all these three values are turning out to be same, I'll say that the function is continuous. In order to call a function a continuous function, you need to ensure that its LHL, RHL, and its value at that point should be same. Then only you'll say that the function is continuous. We'll talk more about that. Let me give you more clarity, more points on that front regarding continuity. Let's say f of x, limit f of x when x approaches a from left hand side and right hand side both exist, but if they are not equal. So if they are not equal, of course, the prerequisite, the basic condition for a function to be continuous is LHL, RHL, and the value should be same. So even if they exist, even if they are finite, but if they are not equal, we cannot say that the function is continuous. It will be discontinuous at that point. Here, let's say left hand limit at a of f of x, right hand limit at a of f of x exist and equal, but it is not equal to f of a. Then also it will be discontinuous. If f of a is not defined, let's say f of x from left hand side, f of x from right hand side of a is defined, it exists. It could be same, it could not be same. But what if f of a is not defined? If f of a is not defined, then of course it will again go discontinuous at that point. 10x at pi by 2. Can you not see that example here? At least when the limit doesn't exist. Let's say RHL exists. The value of the function also exists, even if they are equal. But what if LHL is approaching infinity? Then again it is not defined. So in that case, LHL is not equal to RHL and the value of the function. Then again you are saying that the function is discontinuous. In a very simple language, you should keep this thing in mind. If LHL, RHL, and the value of the function is equal, the function is continuous. Otherwise, not. Otherwise, not. Did you understand my statement very clearly? Now, moving ahead with more conclusions. Here, this is exactly what we have discussed so far. But here, I'll give you some more cases that how do you talk about discontinuity, right? So this is another case. Graphically, if I could tell you that at A, see, the left hand limit is taking it towards L1. The right hand limit is taking it towards L2. And the value of the function at A is L2. So RHL and the value of the function is same at A. But LHL is not same because LHL I hope you are seeing is leading me towards L1. And that's a classic case of discontinuity. I hope you are seeing that the function is taking jump from this point to this point. I hope you are seeing this jump, and because of that, the function is getting discontinuous. I hope you all are realizing the different scenarios I'm trying to give you. Look at this scenario of discontinuity. Again, in this case, you would say at A, LHL and RHL both are equal to L, but the value of the function is different. So in this case, LHL and RHL were equal, but the value of the function was different. And then again, I'll say this is another case of a function being discontinuous because it broke. The graph was like this, and then this. So the graph broke at this point. There again was a jump. And in that case, I'll say that the function got discontinued. Now, in this particular case, let's say the function is not defined. So the left hand limit says that the function is approaching L. The right hand limit says that the function is approaching L. But at A, the function doesn't exist at all. So left hand limit conveyed that the function is going in that direction. The right hand limit said that the function is going in that direction. But at that point, the function didn't exist. And if that is so, then I'll again say that the function is discontinuous. Are you understanding these scenarios? So I hope you have gotten a great clarity. Now we'll talk about different types of discontinuity. In questions, you deal with different kinds of discontinuity, then you're supposed to define them. And if any fixing can be done, those fixes are also what we'll be discussing now. For example, there is a type of discontinuity which is called removable discontinuity, which means the function is discontinuous, but its discontinuity can be removed, and after removal of that discontinuity, the function can be converted into a continuous function. How is that possible? Let's discuss that. So majorly or broadly, we categorize discontinuity into two categories: removable and non-removable. Removable means the function can be made converted into a continuous function. But when you talk about a function being having a non-removable discontinuity, which means no matter what you do, the function cannot be converted into a continuous function. So we'll talk about these two discontinuities in detail, and we'll see a better or a broader distribution of this kind of discontinuity. So first of all, let's begin with removable discontinuity, where we broadly categorize into two categories: missing point and isolated point. What are they? Let me explore that point. Look at this particular function. The function is defined as x minus 1, 9 minus x square upon x minus 1. So they have deliberately given this x minus 1 and x minus 1. You just cannot cancel this x minus 1 by x minus 1, because they have tried giving you the idea that yes, it may be the graph of 9 minus x square, but because of this x minus 1, they are trying to ensure that 1 is not there in its domain. You cannot say that, sir, x minus 1 is cancelled by x minus 1. That will be mathematically wrong. This function is defined like this. So they have deliberately given x minus 1 in the denominator. And when they say so, they are trying to give you the hint or the idea that 1 is not there in the domain of this function, which means at 1, it is not defined. At 1, the function is not defined. So technically, the function is 9 minus x square only, but at 1, it goes not defined. So I'll draw the graph of 9 minus x square only, but at 1, I'll remove the existence of the function. And I hope you can see, since it is a parabola 9 minus x square, it is continuous everywhere. Even at 1, its left hand limit and right hand limit will also take me to a point. But again, the problem is at 1, it does not exist. So this is a missing point discontinuity. And to remove that, I'll say that, sir, f of 1 should be the value of the function. F of 1 should be taken as, let's say this x minus 1 is not there. So 9 minus 1 square, which is 9 minus 1, 8. So if I redefine this function such that, it is x minus 1 upon x minus 1 times whole of 9 minus x square for all the values of x excluding 1. But when x is 1, it should be 9. So now what I have done is I have redefined the function. So when x is 1, it is becoming, sorry, not 9, it is becoming 8. So when x is 1, it is becoming 8. So at this point 8, I have defined it. So previously it did not exist there, but now it exists. And at 1, it is approaching 8, and at 1, it is defined as 8. So the LHL, RHL, and the definition of the function, the value of the function at 1, all three are same. And if all three are same, I'll say that the function is continuous. Did you understand this part? So missing point discontinuity, and I hope you are understanding how should you remove it by redefining the function. Now this is isolated point discontinuity. What does it mean? Look at this example. GIF of x plus GIF of negative of x. We know it is defined as 0 as long as x is an integer. It is minus 1. It is not minus 0. It is minus 1. Let me just correct this. Give me a second, students. It should be minus 1, right? So it should be minus 1 as long as x is not an integer. I hope you remember it. Let's say if I take 2. So 2 minus 2 is 0. But if I take 2.3, 2 minus 2.3 minus 3. So 2 minus 3 is minus 1. Do you remember that? So this function is defined as 0 and minus 1. 0 as long as x is an integer, but minus 1 as long as x is not an integer. So x is not an integer is there. But at these integral points, it will be 0. So at integral points, it will be 0, which means its graph will look like this. At minus 4, it will appear here. At minus 3, it will appear here. This will appear here. So this is an isolated point discontinuity. So what is happening over here is that the function exists. At integral points also, this is not a missing point, the way we have discussed in the previous case. The function exists, its values also exist, but it is taking a jump. So I am seeing when x approaches minus 3 from both these sides, it is approaching minus 1. But at minus 3, it has become 0. So it is a discontinuity first of all. But what kind of discontinuity? Isolated point discontinuity. So the point is isolated. So if I could again redefine this function in a little different manner, that instead of defining f of x like this, I define f of x as minus 1 as long as x is not an integer, and minus 1 when x is an integer, then yes, this discontinuity can also be removed, and we'll categorize it as a removable discontinuity. But for that, you have to make some corrections. Here in that scenario. This is minus 1. I hope you're understanding. Such corrections are needed to be made. So when corrections can be made and the discontinuity can be removed, those kind of discontinuities are called removable discontinuities. That is not a problem. The problem is non-removable kind of discontinuities, because when you deal with non-removable kind of discontinuities, they cannot be removed. For example, finite discontinuity. I'll share it with an example. When you talk about finite kind of discontinuity, let me take an example. Let's say here you have this thing. Let's say this is the graph of a function. This is the graph of a function. So the graph goes like this and it goes like this. Now you cannot do anything with this graph. You cannot remove it even, because see, the LHL is pointing, you are taking you towards this point. The RHL and the value of the function is taking you towards this point. You cannot club them. You cannot join these graphs. If you want to join this graph, it will lose its very definition condition to be a function. So here in this case, this is a discontinuity and you cannot remove it. The function from left of A was like this, and on the right of it was like this. So you cannot club them. To make it continuous, you cannot do that. I hope you are understanding why. Because there is a finite jump here. So this is a finite discontinuity which is classified or categorized as non-removable discontinuity. You cannot remove this discontinuity. It will exist. You cannot remove it. Similarly, the second kind is infinite discontinuity. In infinite discontinuity, there is a very standard case. Let's say that when A minus it is approaching L1, when A plus it is approaching L2, and either L1 or L2 is infinity. What do I mean by that? Let me draw a graph here. Let me draw a function here. Let's say at this point A, let's say this is a point A. The graph of the function goes like this. And then from here, it let's say goes like this. Right. So what do I mean by that? Look at this graph. Sir, when x is approaching A, on the left hand side, it is approaching infinity. I hope you are seeing. When x is approaching A from the right hand side, it is approaching 0. So you cannot again club it, because previously there was a finite gap. Now there is an infinite jump, and because of that, again these two cannot be clubbed, and these two cannot be clubbed, and then these two cannot be joined, which means the function cannot be converted into a continuous function, which means this is again a type of a discontinuity which is non-removable. And being more specific, this is infinite discontinuity because the jump is infinite. In the previous case, the jump was finite. I could measure this jump, but now this is an infinite jump. So this is an infinite discontinuity, which is again a non-removable. What is oscillatory discontinuity? When you talk about oscillatory type of a discontinuity, it means if you draw the graph of f of x is equals to sine 1 by x, the problem is if you draw the graph of this function, it goes like this. Although I won't be able to draw it properly, but still I'll try to show you something here. The graph goes like this. The graph goes like this, and it oscillates a lot here at this stage. What I'm trying to make you understand is that for different values of x, the graph basically it creates a sinusoidal wave. But for different values of x in this very close proximity of 0, this keeps on changing its behavior. So let's say at 0.0001 it is -1 or it is something. Then at 0.00001 it will be something else. So it keeps on shifting, it keeps on shuffling. So you cannot decide its left hand limit and right, because in very small range it keeps on changing. I'll tell you. Go to the internet, draw the graph of sine 1 by x. You have a lot of tools, internet tools. Visit any website, you just type that draw graph online. There will be a lot of websites. In that website, enter sine of 1 by x. And then you zoom in around 0. The more you zoom in, the more these sinusoidal waves, the more close waves you'll keep seeing. And that's where you'll see that the function's nature around 0 cannot be defined, because the limit is not very specific. The limit sometimes will say something, then sometimes it will say something else. It will say something else, it will say something else at different points in very close proximity. And that's where you will be able to conclude that at 0, it cannot be concluded. What does it mean? That at 0, it cannot be defined. What? The left hand limit and the right hand limit. Although the function appears continuous, but it is not actually. I hope you're understanding the wave. It is changing its pattern, its generalization, its trend, its overall future very rapidly. And that's where you cannot define LHL and RHL, and because of that, we categorize it as oscillatory discontinuity, and it again cannot be removed. So these are all the different types of discontinuity. Theoretically, I have tried explaining it. If I could simply tell you the different understanding of the standard functions which we have studied, I'll say constant function is continuous everywhere from -infinity to infinity, which means all the real numbers. When you talk about x to the power n, what do I mean by n? N is an integer, a positive integer or a non-negative integer. It is also basically continuous from -infinity to infinity. All the polynomial functions are continuous. Even x to the power -n, when n is a positive integer, is continuous except for 0, because it is basically 1 upon x. I hope you're realizing. Let's say I'll take an example here. Let me take an example here. Let's say I take the value of n as 2, so it is 1 by x square. So the function is 1 by x square. Now you must realize 1 by x square at 0 is not defined. So yes, it will be continuous from minus infinity to infinity except for 0, because at 0 it goes not defined. Similarly, when you look at mod x minus a, it is continuous everywhere. When you look at any polynomial, it is continuous everywhere. This is something we have discussed while discussing the graphs of these functions as well, while discussing the chapter functions. Do you remember that? Again, when you look at our rational function px upon qx, where px and qx are polynomials, then we remember that qx should not be 0. As long as qx is 0, it will be not defined. So it is from minus infinity to infinity. Only thing which needs to be excluded is the points where qx is becoming 0. The trigonometric functions such as sin x and cos x are continuous everywhere, but tan x is discontinuous at all the odd multiples of pi by 2. I hope you know why. We have discussed it in functions, we have discussed it in trigonometry. If you have still forgotten it, do watch these videos again. But I'm sure you must not have forgotten those, because we have discussed them in a very detailed manner. Now, look at the cot x. Cot x basically gets discontinued at all the multiples of pi, because there, I hope you remember, yes, we are going great. I hope you remember, because there, cos x, basically sin x is not, sin x becomes 0, right, at all the multiples of pi. Look at this, sec x. I hope you remember sec x is reciprocal of cos x. So whenever cos x becomes 0, sec x will be discontinuous. Whenever sin x is 0, cos x will be discontinuous. What about e to the power x? It is continuous everywhere. What about log x? It is continuous in its domain, and its domain is 0 to infinity. I hope you are able to make a lot of sense out of these discussion we were having about the table. Now, I'll talk about some more data, some more algebraic operations based on functions. Let's say I'm given two functions. Then sum, difference, product, and quotient of two continuous function is always a continuous function. So let's say someday somebody says, put your comment on x square ln x continuity. Put your comment on x square times ln x continuity in the domain where x is told to be from 0 to infinity. Then I'll say, sir, x square is continuous from 0 to infinity. Ln x is continuous from 0 to infinity. So both of them are continuous. Then the product, sum, or difference, or even division will also be continuous, except for the part in division, the gx should not be 0. That is something we know that should fulfill the criteria of its domain, right? So that is something which I hope you will remember as a theorem, as a fact. While solving questions based on continuity, if I could determine two functions which are continuous, then why should I check its continuity? Can I not generalize it based on this particular result? I hope you'll remember it, right? Now, moving ahead towards the next case, second theorem, that is more important. If fx is a continuous function, gx is discontinuous at a, then the product function fx dot gx is not necessarily be discontinuous at a. I'm not saying it will be continuous at a. I'm not saying it will be discontinuous at a. It could be continuous or discontinuous. Then what is the point of saying it? The point is that if a continuous and discontinuous functions are multiplied, then it will not be necessarily discontinuous. Usually students infer it like this. So remember this result. I hope you'll understand it. There is an example as well. For example, there is a function cos of 2x minus 1 times pi by 2, and the other function is g of x, which is GIF of x, right? So when I multiply these two functions, let's say there is another function psi x, which is the product of f of x and gx, which is GIF of x times cos of 2x minus 1 times pi by 2. Now please understand, at 1, this is discontinuous. At 1, this is continuous. I hope you remember, GIF at integral points is discontinuous. Fraction part functions at integral points is discontinuous. So this is discontinuous at 1. But it is continuous at 1 because this is cos x basically. So a continuous into discontinuous can be continuous or discontinuous. So at 1, if I want to make comment, I have to check its left hand limit, right hand limit, and the value of the function. And after checking that, checking all the three values, LHL, RHL, and the value of the function, we can now again conclude that this function is going to be a continuous function, which we'll discuss. But you know how to find the limits, and that's exactly what we'll be applying here in that case. Now, moving ahead towards the next theorem, which is theorem number 3. If there are two functions fx and gx, both are discontinuous at a, then the product function fx dot gx is not necessarily be discontinuous. Again, students assume that, sir, if we multiply two discontinuous functions, then the product should be definitely be discontinuous. No, that is not true. It can be continuous, it cannot be continuous. It can be discontinuous, it can be continuous. So there is possibility for both. Remember, when you multiply two discontinuous functions, for example, fx and gx, fx is defined as 1 and minus 1 for positive and negative values respectively, and minus 1 is 1 as gx for positive and negative values respectively. If I take their products, the product is going to be minus 1, which is for all the values, and this is a continuous function. This was discontinuous at 0. This was also discontinuous at 0. I hope you can see that the function is changing its value. But at 0, this product, f of x and gx, two discontinuous functions product, became minus 1, which is a constant function which is continuous at 0. Are you understanding all these things very clearly? Are you noticing these theorems which I'm trying to demonstrate here? And if you have understood whatever has been said so far regarding continuity, let's check your understanding through this particular question. What does it say? JEE Mains 2025 has asked it. It says number of points of discontinuity of this function. So this is a sum of two functions which are discontinuous at their own points. So of course, at all the points where this is discontinuous, at all the points where this is discontinuous could be possibly the points where this could be discontinuous, right? So let's try and figure it out. So as we have discussed that this is a GIF, right? And whatever is there inside the GIF, we know that this part should not be an integer, because whenever it becomes an integer, the points of discontinuity will arise. I hope you're understanding this concept. Now, how do I identify that at what values of x will it be becoming an integral value? Will it be taking an integral value? And so that I could figure out the points of discontinuity. Let's follow a very simple step. First of all, please understand that between 0 to 4, what we need to figure out, okay, that's something we'll take care of. But first of all, let's look at this part, x square by 2, and then we'll look at the other part, root x, because both of them are individually inside the GIF sign. So first of all, let's deal with x square by 2. So when you say that x square by 2 is there, we know it very clearly that x square by 2 should not be an integer, right? So we know that x square by 2 should not be an integer. Great. Now, let us find that when will it be an integer. Those points will exclude, or those points will count, because those are going to be the points where it will be discontinuous. So let's say x square by 2 takes some integral value. So let's say it takes a value, let's call it z1, where we know that z1 is an integer. I hope you are able to understand my point very clearly here without any confusion. Now, what I say next is, if x square by 2 is z1, can you say something about x square? You'll say x square will be 2z1 and x will be plus minus under root over 2 times z1. But I need not put a plus minus sign, because we know that we need to check the value for the values of x which are between 0 to 4. So I need not take the negative values of x. I hope you're realizing it here. So I'll keep it as under root over 2 times z1. Now, how do I verify or validate? I know that z1 is an integer. So can we try some integral values of z1? So let me try some integral values of z1, and for which let me see that what values of x do I get, right? So first of all, when I try z1 as 0, because that is the least possible value I can try, because I cannot go before, I cannot have values less than 0, because if I take z1 as minus 1 or something like that, it will not be satisfied here. So I need to take z1, I need to begin with z1 as 0 only. I cannot have lesser values than that. So if I begin with 0, 2 into 0 is 0, which is under root of 0, that is 0. So the first point of discontinuity could be 0. I'm not saying this will be 0. I'll have to be more careful, because this 0 is actually lying on the boundary condition. This is the left. I hope you're realizing x is what we need to keep between 0 to 4. So 0 and 4 are at extremum. What does it mean? That at 0, the discontinuity may or may not exist based on what? Based on the right hand limit at 0, the right hand limit at 0, and the value of the function at 0. Because at 0, I did not check its left hand limit. I hope you are understanding this concept. The same I'll do for 4 as well, because at 4, I won't be evaluating the right hand limit. At 4, I'll be evaluating the left hand limit and the value of the function. If these two are same, I'll say that at 4 it is continuous. So at 0 and 4, the points of discontinuity could be or could not be. So I need to be more cautious and careful. I hope you're understanding why. So here I'm considering 0 as of now. I'm putting it under those list of suspicious points, and then of course in the end I'll verify it. Right. Now, when I move ahead with 0, I'll try z1 as 1, that 1 into 2, that gives you root 2. Then when you try z1 as 2, 2 into 2 is 4, under root over 4 is 2. So these are all the values of x I'm working upon, right? So we know that x goes till 4. So I need to keep trying the different values of z1 until I attain 4 or a value close to 4, right? Now, if I try 3 here, I have tried 2 here, 2 into 2 was 4, square root of 4 was 2. Then if I try 3 here, it will be root 6. If I try 4 here, it will be root 8, which can be said a value as 2 root 2. When I try 5 here, it will be root 10, which will be root 10 only. When you try 6 here, it will be root 12. Root 12 is basically 4 into 3, which is 2 root 3. I hope you're understanding it. When I try 5 and 6, when I try 7, it will be root 14. You cannot do with that, anything with that. So that is root 14. When I try 8, 8 into 2 is 16. Square root of 16 is 4. I hope you're realizing I need not try any further values of z1 because this is the other boundary condition. If I try further values of z, then I'll start getting the values which are greater than 4, which I need not bother about. First of all, you need to understand that at these points, which points, students? Root 2, 2, root 6, 2, root 2, root 10, 2, root 3, root 14. This x square by 2 will be becoming an integer. And at these points, if it is becoming an integer, this GIF will be discontinuous. It will become a discontinuous function, or it will break. The graph of the function will break. So of course, without any hesitation, you can include these points when you talk about the points of discontinuity of this function. But I hope you remember 0 and 4 could be or could not be. Based on what? Based on some more verifications, which we'll do later. As of now, let's work on some more results. Which results? Sir, there was one more possibility from where you could have drawn more conclusions based on the discontinuity of this function. What were those points? I'll say, sir, this is under root x. If this is under root x, then under root x is inside the GIF sign. So whenever under root x takes the integral values, then also the function will become discontinuous. So I'll say that here, whenever root x becomes or takes an integer value, then also it will be discontinuous. So let's say there is another integer z2, which is equal to under root x, right? So from here, I can say that x is equal to z2 square. Did you get that? I'll try different values of z2. I hope I need not try negative values of z2, for example, -1, -2, they'll give you the same values. So I need not try those values. Rather, I'll begin with 0 only. So when you put z2 as 0, you get the value of x is 0, which we have already considered here. Now I'm discarding that. When you try z2 as 1, you get x is equal to 1 square. So that one I haven't considered here. So that is something which I'm considering here. Now, when I move ahead, when I try z2 as 2, because z2 is basically integer. So after 1, 2 was what we are supposed to deal with. So 2 square is 4. That 4 is also we have already considered here. So I think after this, I need not try 3 because 3 square will be 9. And 9 is something I don't want to check because 0 to 4 is what I have the limit as, right? Now, when you move ahead, these are all the points. But now the two vulnerable points which I need to verify would be 0 and 4. So 0 and 4, I need to be more cautious with. Now, how do I deal with that? 0. So I'll find the right hand limit around 0. Of course, in the neighborhood of 0, the right hand limit and the value of the function at 0. So let me first of all find the value of the function at 0. Can you help me with that? I hope there is no doubt in that 0 by 2 will be 0. GIF of 0 is 0. Under root over 0 is 0. GIF of 0 is 0. So 0 minus 0 is 0, which means f of 0 is 0 without any hesitation. Do you all agree with that? Now let me find the RHL. What is the meaning of RHL? RHL means limit x approaching 0 from its right hand side. Now you can, try imagine this by yourself. I'll just write this data in front of you so that you stay more comfortable with that. The function says GIF of x square by 2 minus GIF of under root over x. That's the function. Now try imagining a very small value, a very small positive value, because 0 plus means what? 0 0.1, 0 0.2, something like that. So something like that, a very small value is given over there. So square of that also be very small, 0 0.1, something like that. Even 0.1 by 2 will also be that something very small value, 0.1, something like that. And GIF of that very small value will be 0. So this is going to be 0 in the neighborhood of 0 plus. Similarly, under root x. Under root x means what? 0.1. Under root of 0.1 will also be very small. And the GIF of that very small value like 0.1 only will be 0 only. So yes, it is 0, the value of the function. And the RHL, the right hand limit, is also 0, which means that it is not discontinuous here. Are you understanding? First of all, you need not find the LHL here because it's the left extreme of that interval. So here in this case, I will not be finding the LHL. Although I hope you must have understood and realized that all these points, at all these points, including this one, it will be discontinuous because they are becoming or taking integral values. So whenever they become integers, they will go discontinuous. They will become discontinuous, right? But the problem is at 0, it is not discontinuous because 0 at 0, I'll be checking the RHL, the right hand limit, and the value of the function, and that is turning out to be same. And if the RHL and the value of the function at this left extremum 0 is turning out to be same, which means it is continuous. So 0 should be excluded from the list of the points of discontinuity. Did you get that? Similarly, I'll be checking it at 4 now. So how do I check or verify it at 4? I hope you're getting it very clear, very much, you're understanding it very clearly. That first of all, I need to find the value of the function at 4. So f of 4 is what I'll be finding first. What is going to be the value of f of 4, students? I hope you're comfortably understanding. F of 4 means what? 16 by 2. 16 by 2 is 8. GIF of 8 is 8. And that is what? 4. Square root of 4 is 2. GIF of 2 is 2. So 8 minus 2 will be 6. So f of 4 without any hesitation can be said to be 6. Now, what's the catch here? The catch is, let us find f of, now let us find the LHL around 4. So in the neighborhood of 4, I'll find the left hand limit, right? So again, I'll find the LHL in this case. So I'll be saying that limit x approaches 4, but from the left hand side, which is 3.8, 3.9, something like that. On what? On the function, let's say x squared by 2, it's GIF minus GIF of under root x. Now there are two ways, there are two methods. Either you use your intuition and work it out, or you use the basic standard approach. I'll give you the basic standard approach as well, and I'll tell you through intuition as well how can you work it out. You can have both of these methods. Whenever you get confused, you follow the standard method. But if you are able to calculate things with more clarity through your intuition, I will always give you this liberty that use this, avail this, use your intuition. How? We'll discuss both, right? Now, first of all, I'll say that standard method, what does it say? Let us say that x approaches 4 minus. So what I'll do is, I'll replace x by 4 minus h. And I'll say that here h is a very small quantity. H is a very small positive quantity, which means I'll say that h is now approaching 0. And that is a very small positive quantity because 4 minus h will be x. I hope you're realizing why. So I hope you are understanding it very clearly that when I replace x by 4 minus h, I'm considering a very small value close to 4. I hope you are understanding very small less value close to 4. That means 3.8 to 3.9, something like that. So yes, now this entire expression can be written as limit h approaches 0. And here we'll say x gets replaced by 4 minus h whole square divided by 2 minus GIF of under root over 4 minus h. From here only you can conclude that, but even if you get confused, you can work out more. But from here only you can say a lot about this. What am I saying here? I'm trying to give you a very simple result. Try and understand. Imagine that this h is very small, which means this will be what? 3.9 or 3.8, something like that. Even when you square it, just do this thing very clearly that even when you square it, something like 3.8 to 3.9, you'll get a value. And you need to half it, and then you'll get a value, and then you take the GIF of it. Similarly, let's imagine a value or a square root of 3.8, a very close or approximate value of under root of 3.8. And from that, when you take its GIF, you can find the value, which is the intuition-based method, which is, of course, will always carry with us. But let's say I don't want to use that. I want to use the conventional method. Then what do I do? I'll simply say that expand this 4 minus h square. What does it become? On the next page, it becomes 16 plus what? We'll have h square minus what? 2h. I hope there is no confusion on that. 16 plus h square minus 2h. Whole divided by 2. I need to take the GIF of this. Right. I hope there is no confusion on that. And there limit h is approaching 0. Minus under root over 4 minus h. So GIF of under root over 4 minus h. I hope there is no confusion on this part. Now, let us try and decide which one is greater between 2h and h square. I hope that will give you a great clarity. So I hope you must realize that h square, if h is very small, will be less than h. And this is 2h. So h square will be less than 2h. I hope you are understanding in terms of magnitudes. So h square minus 2h will be something very small. I hope you're understanding it. So this will be 16 minus something very small. This is 16 minus something very small, something like 15.8, let's say, for a while. And when you take half of 15.8, let's say, for a while, it will be 7.5, 7.6, 7.7, something like that. And when you take the GIF of it, it will be 7. Did you get that part? I hope you're able to make a lot of sense out of it. Similarly, when you try to find the square root of this part here, please understand, square root of 4 is 2. Square root of 4 is 2. Square root of 1 is 1. So here what you need to understand is the square root of 4 minus something. I repeat, if you are not able to imagine this, I'll tell you that square root of 1 is 1. The square root of 4 is 2. So if I have something between them, let's say if I have something between them, for example, this square root of 4 minus h, then do you not agree that that value will also lie between 1 and 1 and 2? And let's say that is 1.2 for a while, and 1.2, 1.7, 1.8, anything like that. And if I take the GIF of it, do you not agree that GIF of under root over 4 minus h, where h is a very small value, then it will be something like 1.8 or 1.9, something like that. And GIF of that is going to be 1 only. And from that, I'll say that 7 minus 1 is going to be 6. This is all you could have done through intuition only from this step only. You need not do all this, right? So this gives me the value 6. Again, the problem here is the value of the function and the LHL both are same, which means the function at 4 is not discontinuous. So this 4 should also be discarded. Did you understand my whole point? So what I'll say is that if I were to answer this question, that the total number of points of discontinuity would be 1, 2, 3, 4, 5, 6, 7, and this one 8. So there would be total 8 points where this function is becoming discontinuous. Are you able to make a lot of sense out of this? I hope there is no confusion or hesitation on that. Now, once you have gotten clarity on this front, let us move ahead with the next topic, with the next funda. What is it? It is intermediate value theorem. This is a very straightforward theorem, very clear theorem. You need not put much efforts in understanding it. There are 3 graphs, let's say. All of them are continuous. Let's say the graph could go like this, the graph could be a straight line like this, or graph could be a curvature like this. But what you need to understand is that the graph is continuous. So first of all, what we know about this graph is that the graph is continuous in the interval a to b. The interval is closed interval. Now here, what we know is that f of a and f of b are not equal. So for example, if you look at f of a and f of b, they are not equal. Even the other case also, if I take f of a and f of b, they are not equal. Even if I take the third case where this is f of a and this is f of b, they are not equal. So these are all the other possibilities. Now, what intermediate value theorem says? You will say, sir, this is very obvious. What I'm going to say next is going to be very, very obvious now. What you can say is, or what the theorem says is that there will exist a C, a value between f of a and f of b. There will exist a C, a value between f of a and f of b. There will exist a value C, a value between f of a and f of b. There will exist a value C between f of a and f of b such that there is at least one number x naught in a to b. So there will be a number between a and b, x naught, for which a C will definitely exist between f of a and f of b. There will exist an x naught between a and b, for which there will be a C between f of a and f of b. There will be an x naught, there will be at least one x naught. There are many, of course, in this case, but there will be at least one x naught between a and b, for which there will be a C between f of a and f of b. Now, I hope this is very obvious, because if it wants to go from a to b, where it is f of a to f of b on the y-axis, then there will be a value between f of a and f of b, let's say C, for which there will be an x naught, for which f of x naught will be C. And that x naught will lie between a and b. So there will be at least one x naught like that. This is something very much understandable, I believe so. So nothing needs to be proved. This is clearly observed and understood by all of us, I think, through this simple illustration only. Now let's talk about the other case. When I talk about, let's say, if I define a function, of course, as its piecewise definition, where I categorize it into rational and irrational numbers. What I'm trying to say here is that, let's say that we know that, let's say I take two numbers, 1.1 and 1.2. Can I say between 1.1 and 1.2, there are infinite rational and irrational numbers? So let's say if I were to define a function like this, if I were to define a function like this, let me take this here only, where f of x is defined as x whenever x is a rational and f of x is defined as 0 whenever x is irrational. Are you able to imagine its graph? Are you able to imagine its graph? I'll take another example. Let's say here, I'm saying that f of x is defined as 1 and minus 1. It is 1 whenever x is rational and it is minus 1 whenever x is irrational. So I hope you're realizing the point is very simple, that even if I draw its graph between, let's say, 1.1 and let's say this is 1.2. I have drawn it very much very much little far away to, let's say I have zoomed it in so that you can understand it more clearly. So between 1.1 and 1.2 there will be a lot of points which will be rational and irrational. So at some points it will be 1, at some points it will be minus 1, then 1, then minus 1, then 1, then minus 1. So are you realizing that it clearly is going to be a discontinuous function? Because let's say even at 1.11, if it is 1, then next to 1.11 there will be an irrational number, and at that point it will be minus 1. Just before that there could be an irrational number, it could be minus 1. Right after that there will be a rational number, and there are infinite rational and irrational between those numbers as well. So it will be 1 minus 1, 1 minus 1, 1 minus 1. It will be oscillating between 1 and minus 1. So I hope you're realizing that it may look like that you have drawn two parallel lines when you look at it from a broader perspective, but when you zoom it in, you will see that it is clearly a discontinuous function. It is oscillating like that between 1 and minus 1. So my point is very simple, that whenever such definitions are given, you use this funda that, let's say, if fx is defined as x for all the rational values and 0 for all the irrational values of x, can it be continuous anywhere? It could be. Where? It could be continuous when this and this become equal. I repeat, if x and 0 become equal, which means if x is 0, what is the advantage of that? Sir, if x is 0, in that case, when x is rational, then also it is 0. When it is irrational, then also it is 0. So in the neighborhood of that rational, there will be irrational numbers. In the neighborhood of those irrational numbers, there will be rational numbers. So around 0, it will be 0. Did you get my point very clearly? Because please understand, at 0 it is 0, but even around 0 it will be 0. Because in the neighborhood of 0, there are some rational and irrational numbers, infinite rational and irrational numbers. At those, it will be 0. So of course, even at 0 it is 0, and in the neighborhood of 0 also it is 0. And that's why I'll say that it is continuous at 0. So how do you find the points of continuity of such functions? Although they'll be discontinuous everywhere, except for some points. For example, look at this example. Here I want to say that where would it be continuous? I'll say the point where x and minus x are equal. So when do we see x and minus x to be equal? So if x is equal to minus x, 2x is equal to 0, which means x is equal to 0. So again, when x is 0, at that point it will be continuous. Why? Because see, let's say when x is 1, it will be 1. But in the neighborhood of 1, it will be minus 1. So 1 and minus 1, it is clearly discontinuous. But at 0, what do you see? At 0, it is 0. Even in the neighborhood of 0, it will be 0, because minus of 0 will be 0. So that's how I can say that it is becoming continuous. On the same grounds, can you not say something about these functions as well? For example, this function. This is defined as x whenever x is rational. This is defined as 1 minus x whenever x is irrational. What can you say about its continuity? You will say, sir, when this x and 1 minus x are equal, then it will be continuous. So if x is equal to 1 minus x, I can say that 2x is equal to 1, which means x is equal to 1 by 2. So 1 by 2 will be the point where it will be continuous, except for 1 by 2. At all the other points, this function is going to be discontinuous. Did you get that? Similarly, let's say if somebody says that x square in 1, x square when x is rational, 1 when x is irrational. When will it be continuous? I'll say whenever x square is 1, which means whenever x is plus minus 1, it will be continuous. So except for 1 and minus 1, it will be discontinuous everywhere. Did you understand this whole definition? Did you get a great clarity on this? Let us understand through it all of this, what we have discussed so far, through one more example, one more question. This question says that this is a function and it is continuous at x is equal to 0. What does it mean? If it is continuous at x is equal to 0, then its left hand limit, right hand limit, and the value of the function at 0, all three should be same. And if it is said to be continuous, why should I explicitly find LHL and RHL? Why can I not simply find the limit of this function when x approaches 0. That should also work. So let's find that only. So I am finding limit x approaches 0 on this function. So when x approaches 0, that is in the neighborhood of x, when x is not exactly 0, this is the definition I'm supposed to choose or pick. So that definition says it is ln 1 plus 5x minus ln 1 plus ax or alpha x, it is alpha, let's say for a while, whole divided by x. So that x I'm distributing to both of them individually. I hope we can do that. There is no problem at all in that. Now, when you do so, what advantage do you get? The idea is very simple here, students. What I'm seeing here is that ln 1 plus x upon x, when x approaches 0 is 1. So I'll use that. But here it is 5x. So I should have a 5x here. So I need to multiply it by 5 here as well in the numerator. Similarly, it is ln 1 plus alpha x. So I should have alpha x here as well in the denominator. So I have multiplied by alpha in the denominator. I should multiply it in the numerator as well by the same value alpha. Did you get that? Now, I hope I did not tell you this part, that when x approaches 0, this will approach 1. When x approaches 0, this will approach 1. So this is clearly going to be 5 minus alpha. This is going to be a value 5 minus alpha. So we got that limit x approaches 0 on this function is 5 minus alpha. But it is continuous at 0, which means this limit should be equal to the value of the function at 0. So the value of the function at 0 is 10. So from here, if 5 minus alpha is 10, what I'll say is that alpha will be 5 minus 10, which is minus 5. And that's your answer in 2 steps. Did you understand this solution? Did you get this entire question? Are you able to make some sense out of it? I hope you will remember such learnings, whatever you are told, and you will apply these learnings in the questions as per the need of the question. Moving ahead, let's start discussing differentiability. So before I could explain differentiability, I'd like to give you more clarity on it by taking a scenario here. Please understand, let's say there is a function. So this is the graph of that function f of x. Let's say this is the graph of that function f of x, this over here, right? And there is a point A on the x-axis. Now we have moved to the concept of differentiability. So we started with limits, we have discussed continuity, and now we are discussing differentiability. So in differentiability, what do we see? Let's have a look at that. In differentiability, let's say there is a point A. There is a point A here. I hope there is no confusion on that. Now, in the neighborhood of A, there is a point A plus h on the right hand side. In the neighborhood of A, there is a point A minus h on the left hand side. So h distance right and h distance left, there is a point A plus h and A minus h in the neighborhood of A. Now, what I do is, I hope there is no hesitation in saying that at A plus h, the value of the function will be f of A plus h. At A minus h, the value of the function will be f of A minus h. So if I join this point with this point, I'll get a secant here. Can you help me with the slope of that secant? All of you must agree in saying that the slope of the secant will be y2, which is f of A plus h, minus y1, which is f of A, divided by x2, which is A plus h, minus x1, which is A. I hope you're realizing it very clearly. Which in a more simpler language, I can write as f of A plus h minus f of A whole divided by, h. Now this is clearly the tangent of that secant. Now what if I put another constraint that this h start approaching 0? I start bringing this A plus h as close as possible to A by doing this thing h approaching 0, by making this h thing approaching 0. So if this h starts approaching towards 0, which means if h starts becoming as small as possible, then this A plus h will start getting closer to A. So let's say it reaches here, then it reaches here, then it reaches here, then it reaches here. And the moment it reaches very close to A, instead of a secant, do you not agree that I'll get a tangent here? So what I'm trying to say is that this f of A plus h minus f of A upon h, when h approaches 0, when h approaches 0, will give you the slope of the tangent. Now what does it mean? It is simply nothing but change in y with respect to x. I made a slight change in x. X was A, then I made it A plus h, and then I observed the change in y. So previously if it was f of A, then it became f of A plus h. So change in function with respect to change in x, when it is observed, it is called derivative of y with respect to x. Derivative of f of x with respect to x. So derivative means this, but that is the standard definition that when you want to observe the change with respect to some other variable. But here, I'm trying to give you the geometrical meaning of derivative. The geometrical meaning of derivative is simple, that if you have a curve and if you find its derivative at that point, at a point on the curve, then that derivative at a point on the curve gives you the tangent, the slope of the tangent drawn to that curve at that point. Did you get that part completely? Now, of course, differentiability must be understood by you all in a very simple sense that yes, sir, whenever somebody says that differentiability has its own meaning, then I'll say that its tangent must exist. Whenever somebody wishes to claim that the function is differentiable, then I'll say that yes, at that point, I should be able to draw a unique tangent. So differentiability in a very simple language, if I wish to explain to you all, then it would mean that if I am able to draw a unique tangent to a curve at a point, then I'll say that yes, the function is differentiable at that point. Did you understand the definition here? All I'm trying to make you understand is a very simple thing. Let's say there is a continuous function like this, and there is a point on it, something like this. And at that point, if I'm able to draw a tangent uniquely, that means the function is differentiable at that point. But to check its differentiability, what I'll do is I'll find its left-hand derivative, I'll find its right-hand derivative. And if left-hand derivative and right-hand derivative are found to be same, if both the secants get converged into that one unique tangent, then I'll say that yes, this is differentiable. For example, look at this curve. Let's say this is a curve, and this curve is having a sharp turn here. Now, what does a sharp turn mean? Sharp turn means if I start drawing tangent from this side, they'll go like this. But if I start drawing tangents from this point, they'll go like this. So clearly, I cannot define a unique tangent at this point on this curve because it has a sharp turn over here. So left-hand derivative will be giving me some different secants, right-hand derivatives will be giving me some different secants. And when the secants are merging into that tangent, then a unique tangent will not be attained by us. We'll be getting different tangents. And that's a problem here in this case. So despite the function being continuous, was not differentiable at that point because a unique tangent could not be defined at that particular point. Did you understand that fact? So if I wish to claim that a function is differentiable, a function being continuous, it's not sufficient. Whenever a function is continuous, you cannot say that the function will be differentiable. The function, despite being continuous, could be a non-differentiable function if this kind of scenario arises. So I hope you're understanding it very clearly that differentiability is totally different concept than continuity. But it also uses the concept of limit only. So limit is there in the core of continuity and differentiability, and that is exactly what we'll use. But I hope you're able to understand these two meanings. First of all, through limits, if I wish to verify whether a function is differentiable or not, what I'll do is I'll find its left-hand derivative, I'll find its right-hand derivative. How do we find the left-hand derivative? We have discussed this particular portion here only. This is how you find the left-hand derivative, and this is how you find the right-hand derivative. What is left-hand derivative? y2 minus y1 upon x2 minus x1. Right-hand derivative, y2 minus y1 upon x2 minus x1. But here y2 will be a minus h, x2 will be a minus h. Of course, y1 will be f of a, x1 will be a. But in this case, when I'm looking at the right neighborhood of a, y2 will be f of a plus h, x2 will be a plus h, y1 will be f of a, and x1 will be a. I hope you are understanding this very clearly. So if the left-hand derivative and the right-hand derivative are same, then I'll say that the function is differentiable. That is a method which you can learn and adapt and apply whenever you wish to solve a question based on differentiability. And through limits only, you can explore such opportunities, which I'm not again making you understand, because we know how to use limits. So you just need to apply this formula and work out whether a function is differentiable or not by using the core concepts of limits only. Now let us look at some more cases based on differentiability, and specifically we'll talk about some more standard scenarios based on differentiability, that what all properties related to continuity and differentiability and other theorems you can work upon regarding this concept differentiability. How? Let's have a look at that. First theorem, what does it say? This theorem says that, let's say, sir, there is a function, it is differentiable at a point, then it is necessarily continuous at that point. But the converse is not true. What do I mean by that? I'll depict and demonstrate it with an example. Look at this. This is a continuous function. This is clearly a continuous function. And if it is a continuous function, what does it mean? Is it necessarily differentiable at 0? Because at 0, I'm seeing a sharp turn. I'm seeing a sharp turn. So if I were to figure out the left-hand derivative, they'll be giving me this as a tangent. But if I look at the right-hand derivative, they'll be giving me this as a tangent. And the left-hand derivative and the right-hand derivative are clearly not giving me a unique tangent or the same tangent here. And that's why I am not able to define a unique tangent at x is equal to 0 on mod x. And that's a problem here, which means at x is equal to 0, mod x is a non-differentiable function. Did you get that? But of course, if I were to talk about its continuity, yes, at 0 it is 0. In the left neighborhood of 0 it is 0. In the right neighborhood of 0 it is 0. Approaching 0, which means it is clearly indicating that it is continuous. So all the differentiable functions are continuous. But all the continuous functions are not necessarily differentiable. That's exactly what I'm trying to give you here through this fact. Will you remember that? Once you have learned this particular result, let's move to the next set of rules, which we have already discussed. I hope you must have also remembered these, that whenever you talk about a polynomial, even degree polynomial, odd degree polynomial, they are some very smooth curves, parabola or something like that, cubic curves and all we have seen. They are continuous everywhere. They are differentiable everywhere, which means at all the real numbers between minus infinity to infinity. I hope you'll remember that. Now, exponential functions, for example, a to the power x or e to the power x, they have very smooth curvature. They are very smooth curves, so they are differentiable everywhere. Of course, they are continuous everywhere. What about constant functions? A constant function is a very simple function. It is a constant function, a straight line, a parallel line, a line parallel to the x-axis. It will have its unique tangent defined everywhere, whose slope is going to be 0 because it is parallel to x-axis. So of course, it is differentiable at all the real numbers. What about logarithmic function? Again, a very, very smooth curvature. It shows the logarithmic function depending on its base. But here again, between 0 to infinity, log x is defined. And again, if you look at this function, between 0 to infinity, it is differentiable and continuous. Similarly, when I talk about trigonometric functions, for example, sin x and cos x, very smooth graphs they show. So of course, they are continuous and differentiable. But if you look at 10x, then don't say that 10x at pi by 2 will be differentiable. No, at pi by 2, it is discontinuous. Pi by 2 is not even in its domain. Then at pi by 2, I won't put any comment on its discontinuity or non-differentiability because pi by 2 is not even in its domain, right? So we are looking at the functions in their domain. So trigonometric functions, all the trigonometric functions are differentiable in their domain because they have very smooth curves. For example, inverse trigonometric functions, they are also differentiable in their domains. Did you get that part? Moving ahead towards this next conclusion, this is something very crucial. The way we have discussed in continuity, that same interval theory we'll discuss in the sense or in the context of differentiability as well. How? Let's say I wish to make my comment on a function's differentiability in the open interval a to b. Then all I need to ensure is that this function remains differentiable in the open interval a to b, which means I need not check its differentiability at a and b. I need not check its differentiability at a and b. But let's say there arises another case when somebody wants us to check a function's differentiability in the closed interval a to b. In that case, I'll say that it will be differentiable or derivable at the endpoints a and b if it is differentiable from the right at a and from the left at b, same as continuity. I hope you're realizing. Let's say there is a closed interval a to b. Then of course, in the open interval a to b, it should be differentiable at all the points. Along with this, two more things you should be able to check. First one is the right hand derivative at a should exist. Second one is the left hand derivative at b must also exist. So if those two values are also there, if these two values also exist, the right hand derivative at a and the left hand derivative at b, if these two values also exist, then I'll say that this function is differentiable in the closed interval a to b. I hope it is completely and clearly same as what we have discussed in continuity. Now, moving ahead, let's talk about a question. Through this, we'll get more clarity. Now, this question may look like a question based on differentiability and continuity, but I'll say if you have learned functions, if you have understood the chapter quadratic equations, you can solve it with some simple steps, with some simple efforts, with some standard graphical transformation formulae. Now, what do I mean by that? Let me rewrite this question first of all. So the question to me looks like a simple question where it says that it is given as f of x, which is given by mod of 2x square plus 5 times mod x minus 3. Right, there is no problem in that. But do you not remember that we have learned that, sir, when you write mod x square or even if you write x square, both are fine, both are same. We can treat both of them as completely and absolutely same. So in that case, can I not replace this x square by mod x square here? This x square by a mod x square here. So I am writing it as mod x square like this. Why did you do it? Now, the reason is pretty simple. Let me try and help you understand this particular flaw here. That let's try and draw the graph of 2x square plus 5x minus 3. So let's say there is a function which is 2x square plus 5x minus 3. This is clearly a quadratic, a parabola will be there. So let me try this function. Let me try finding its roots so that I can draw a more proper curvature of this function by quadratic equation. So I can see that 2 into 3 is minus 6 and 5. So yes, I can split it as plus 6 and minus 1, which means it can be splitted and I can find its roots. So here I'll say that the roots are going to be, the quadratic can be written as 2x square plus 6x minus 3. So if I'm splitting it, I'm taking 2x common from here. It leaves me with x plus 3. So I took 2x common from there and I'm taking minus 1 common from here. So I'm left with minus 1 from here. So of course, the roots are going to be minus 3 and 1 by 2. So if I were to draw its graph, its graph would look somewhat like this. This will be, of course, our y-axis. Without any confusion, this is going to be the x-axis without any hesitation. And now if I were to draw its graph, minus 3 and 1 by 2. So it will look somewhat like this. Minus 3 and 1 by 2. I hope you're realizing it very clearly that here, this will be its minima exactly between minus 3 and 1 by 2. So this is a point minus 3 and this is a point 1 by 2. Did you get that? I hope there is no confusion on that. But I don't want to draw this graph. Although this is a graph, let's say this is a function. Let's say instead of y, this is a function gx, right? Can you help me in drawing the graph of g of mod of x? I hope you remember that f of mod of x or g of mod of x, if I wish to draw, all I need to do is here, for all the values of x which are there on the negative side of x-axis, which are on the left-hand side of the y-axis, those values wouldn't exist anymore because mod x will make that value of x positive. So if I try 2 or minus 2, it will give me the same values. So I hope you remember, even while discussing the chapter functions in the topic transformation of graphs, we had a discussion here that this portion of this graph should be removed and the mirror image of this right part of this graph should be taken with respect to the y-axis whenever you wish to draw g of mod of x. I hope you remember it. So I'll take this mirror image over here, and if I take this mirror image over here, it will be drawn something like this. I hope it looks similar, the mirror image. So this is now g of mod of x. I hope you have no confusion, no doubts on that. But sir, the problem is we are not interested in g of mod of x. We are actually interested in mod of g of mod of x. Actually, we are interested in mod of g of mod of x, and that is exactly our function f of x is. That is exactly our function f of x is. So now when you put a mod over this f of x, what change do you bring here? Now again, when you put a mod over this function, which means it will not take any negative values, which means the part of this function which was lying below the x-axis won't exist. And at all these values, I'll be seeing their replicated positive values, which means the part of the graph which is below the x-axis should be removed. The part of the graph which is below the x-axis should be removed, and it should be reflected by treating x-axis as the mirror. So I hope you're realizing this point clearly is going to be minus 1 by 2 and this is 0, and this is how the graph of f of x will look like. This is how the graph of f of x will look like. Now, why did I draw it? What is the need of drawing it? Most of you must have already realized, sir, that between minus infinity to infinity, if you look at this graph, this is clearly continuous. This is continuous everywhere. You need not say anything about its continuity because from minus infinity to 0, from 0 to infinity, it is clearly Continuous. I need not lift off my pen. The graph does not break. It is clearly continuous. So from minus infinity to infinity, it is continuous everywhere. And if somebody asks me that the number of points where it is not continuous, I'll say 0. I'll say 0. So the value of m is going to be 0 because it is continuous everywhere. Now they are asking you the points where it is not differentiable. So we have learnt that differentiability is a very simple concept. Through RHD and LHD also you could have done it, but I'll say through graphs it can be done within seconds. How? Now since it is continuous everywhere, it could be differentiable everywhere except for the points where it is having sharp turns. And I can very clearly see this function is having sharp turns at minus 1 by 2, at 0 and at 1 by 2. Do you all agree with this? This function is having sharp turns at these 3 points, minus 1 by 2, 1 by 2 and 0. So if somebody asks that at how many points is it non-differentiable, I'll say at 3 points. I'll say at 3 points. So what they are asking you, m plus n. So m is 0, n is 3. So answer should be 0 plus 3, which is clearly 3. Did you understand this whole explanation? Did you understand this entire question without any confusion? Can I move ahead from this now? Now, when you move further, what you see is some theorems based on differentiability. As we have discussed in continuity, let's say there are two functions f of x and g of x. Both are differentiable at a point x is equal to a. Then their sum, difference, product and division will be differentiable at x is equals to a, except for a change that the g of x should not be 0. If at any point if gx is 0, then the function will be not defined. So remember, whenever you add, subtract, multiply or divide two differentiable functions, then that result is also differentiable at that point. I hope no confusion in that. For example, sin x and cos x. Sin x individually is differentiable. Cos x is also differentiable. So what about sin x plus cos x? It will also be differentiable. That's how simple it is. Now, moving ahead, the next theorem says if fx is differentiable at x is equal to a and gx is not differentiable at x is equal to a, then can you say something about fx plus gx or fx minus gx? Yes, it will be not differentiable at x is equal to a. But if I wish to make my comment, on their product, for example, let me bring another theorem here. Let's say fx and gx are two non-differentiable functions. Fx and gx are both of them are two non-differentiable. Previously, what was there? Previously, we had one of the functions was differentiable, other was non-differentiable. Then their sum and the difference was non-differentiable. Perfect, great, we understood that. But if both of them are non-differentiable, then nothing can be said about the sum difference product of those functions. Please remember that. We have kept the examples as well. For example, look at this part. Sine of mod of x is not differentiable at x is equal to 0. G of x is equal to, I would say mod of x should have been written over here. So it is mod of x. G of x is equal to mod of x is also not differentiable at x is equal to 0. So yes, sine of mod of x plus mod of x is not differentiable. Sine of mod of x minus mod of x is non-differentiable. Now this is simply an example that it could be differentiable, it could not be. You can take a lot of examples in that case. You cannot say anything about that. What? If two non-differentiable functions are added, subtracted or multiplied, that product could be either differentiable or not differentiable. You have to work it out. You have to find it out. You cannot straight away put or make any comment on that. There comes another theorem which says that if f of x is differentiable at x is equal to a, and if f of a is 0, and if g of x is continuous at x is equal to a. Three checks I'm putting. Remember, JEE loves this particular case. This is the scenario which JEE loves asking. Basically, in this particular case, I have tested three conditions. Which three conditions here, students? First condition was that f of x was differentiable at x is equal to a. First condition. Second condition, at a this f of x, which means f of a was 0. Third condition, g of x should be continuous at a. Then what? Then f of x into g of x will be differentiable at a. You need not verify it. What is the advantage here? Even if g of x is non-differentiable at a, that let's say even if you have not even figured it out, let's say you're not even aware about gx differentiability at A, then also without testing its differentiability at A, you can say, you can put any comment about the differentiability of f of x into gx at A by observing two things, that f of x should be differentiable at A, second, f of A should be 0, and third thing, that g of x should be continuous at A. If these three conditions are fulfilled, then without any hesitation, you can say that f of x into g of x will be differentiable at A. The advantage here is that you need not know the differentiability of g of x at that point A. Without even knowing that, you can say that f of x into gx will be differentiable at A. All you need to know is three things, that f of x should be differentiable at A, f of A should be 0, and g of x should be continuous at that point. Even if you don't know whether gx is differentiable or not at A, then even beyond that, you can say that f of x into g of x, the product of these two functions, will be differentiable at A. This is something IIT JEE very subtly asks, and they love asking you this particular result in their particular scenario. So let's have a look at that part in that case, right? So after understanding this, let us move ahead towards the next part. This is the next theorem, theorem 5. It simply means that, let's say there is a function and it is continuous. So what usually students do is that they assume that the derivative of a continuous function will also be a continuous function, which is not true. I mean, that is not necessarily true, which means if you are having a continuous function, then its derivative could be continuous or it cannot be continuous. But it needs to be verified. So you cannot say or put or mark any comment on its derivative of a continuous function's derivative. Did you get my statement? In a very simple language, let's say there is a function which is a continuous function. So you cannot make any comment on its derivative. That's my point here. I hope you have understood this part. You can understand it with an example as well. Let's say piecewise function is given f of x, which is defined as this if x is not 0, which is defined as 0 if x is 0. And at x is equal to 0, we know that this is continuous. But the problem here is that if I find f dash x, you can find its derivative by using the product rule. And if you check its continuity at 0, it will be found to be a discontinuous function. So that's my whole point. It is not necessary that the derivative of a continuous function will be continuous. It could be, it could not be. You need to verify it. I hope you'll remember this as a fact. Although there are facts, there are some assumptions. So I'm clarifying these assumptions also, because in case if you are assuming it like this, then do take care of it, right? After this, let us move towards the next part, which says the question is there, right? So how do we deal with this? It says m and n be the numbers of points. Again, the number of points of continuity and differentiability, or non-differentiability and non-continuity, okay, of this function, which is defined as maximum of this, okay. So let's work it out, that how can we draw the graph of this function. I think by having the graph in mind, I think I can put my comments on differentiability and continuity of this particular function. Have a look at this part. First of all, do you all agree that if I were to take, let's say, a y-axis over here like this, and if I were to take an x-axis over here like this, I am first of all drawing the straight line y is equals to x, because what you are seeing is you are seeing different curves. For example, I'm seeing a curve y is equals to x, then I'm seeing another curve y is equals to x cube, then I'm seeing another curve y is equals to x to the power 5, and so on until y is equals to x to the power 21. So first thing which you all must have observed is that all the powers are here odd. X cube, x to the power 5, x to the power 7. So all these powers are odd. That's the best part. Why? I'll tell that. But first of all, let me draw this curve here. First of all, I'll begin with y is equals to x. So if I were to draw the curve of y is equals to x, you all must agree that this is basically nothing but a straight line. This is always a straight line, which of course goes like this, passes through origin and makes a 45-degree angle with the positive x-axis. We all know that very clearly. But when I start drawing the graphs of x cube, x to the power 5, x to the power 7, x to the power 9, and x to the power 21, what do you notice? I'll say that all of these curves will intersect at -1 and 1, because they'll be equal at 1, because x at 1, x cube at 1, x to the power 5 at 1, they all are 1. Even at -1, x at -1, x cube at -1, x to the power 5 at x is equal to -1, they all are -1. So at 1 and -1, all of these curves are going to intersect. If I could simply demonstrate, I'll try to give you a very simple example. Let's look at the graph of y is equals to x cube. Let's look at the graph of y is equals to x cube. This is how you draw the graph of y is equals to x cube. Now let's say this question was a question of these two parameters only, maximum of x and x cube. What will you say? Would you not say that, sir, we know that this is the graph of y is equals to x cube and this is the graph of y is equals to x. Now, if I start paying attention to few details, for example, this point over here is -1, this is 0, this point over here is 1. Although I have not drawn it very accurately, but I hope you're able to make or bring a great sense out of it. Now, what I'm trying to make you understand something very clearly here is that I need to find maximum of x and x cube. So between 0 and 1, what is maximum? Can you not notice between 0 and 1, the maximum is this y is equals to x. But after 1 to infinity, after 1 till infinity, the maximum is x cube. The maximum is x cube. Similarly here, between -1 and 0, the maximum is x cube. And between minus infinity and -1, the maximum is x, because this is the upper curve. So if this was the comparison, I would have drawn this graph like this. I hope there is no confusion on that. You are getting a great clarity on that. But the question is not just about x and x cube. It is x to the power 7, x to the power 5, x to the power 9 until x to the power 21. But still, there is a very good scope of you having a great clarity with what I have given or told or suggested right now, right before this particular part. What I'm trying to make you understand is that, please understand, let's say if the graph of x cube between 0 and infinity goes like this, then the graph of x to the power 21 will go like this. I hope you're realizing it will be below or less than x cube, but it will be above than x cube whenever you see it in these intervals 0 to 1 and 1 to infinity respectively. Are you understanding my language very clearly? I'll try to give you more clarity here. Let's say this is the graph of x cube. This is the graph of, let's say, x cube. This here is the graph of, let's say, x cube. Then this is going to be the graph of x to the power 5. This will be x to the power 7, x to the power 9, and this will be x to the power 21. Although it will not be taking a turn like this. This will be like that, in that direction only. But to show it to you, I am drawing it with more clarity here. And all I'm trying to make you understand is the higher power of x you take, the lesser value it will have between 0 to 1. I hope you all know it. But from 1 to infinity, the higher power of x is there, the higher value it will take. We all know this. So that simple phenomena I'll use. So whenever you look at the values between 0 and 1, x to the power 1 will be the greatest among x to the power 1, x cube, x to the power 7 and all. But between 1 and infinity, x to the power 21 will be the greatest. Are you understanding this? So instead of drawing all these curves and confusing you all, can I not just compare x and x to the power 21? Because all these intermediate curves are not going to play any role at all. You need to decide between x and x to the power 21, because all the other curves will lie between x and x to the power 21. So the extremes will be decided by x and x to the power 21. Did you get that part? I hope there is no confusion on that. So here, let's say we have -1. This point here is, let's say, 1. This, of course, is 0. So you will have this curve going like this. And you will have this curve coming like this. I hope there is no confusion on that. And this point, of course, is going to be -1. I hope there is no confusion on that. Right, so this point over here is going to be 1. I hope you have gotten a great clarity that this will be y is equals to x cube. This is going to be y is equals to x. All the other curves will lie between x cube and x. So here, all the other curves, if you look at all the other curves, they will be here only here. All the other curves will lie between them. All the other curves will lie between here and here. All the other curves will lie between here and here. They will be lying here and here only. So they won't decide the maxima here. The maxima will be decided with the help of x and x to the power 21. Right? It is not x to the power 3. I'm really sorry for that. It is x to the power 21 now. I hope you are understanding this very clearly. Now, when I talk about maxima, can you not see the curve which is above will be the maximum? So how do I decide it? The above curve. The curve which is lying above between minus infinity and minus 1 is y is equals to x. Can you see it very clearly? So I'll take this above curve, right? I'll draw this above curve. So the above curve here is this y is equals to x. Then the curve which stays above is this y is equals to x to the power 21. Then the curve which stays above is y is equals to x between 0 and 1. Then the curve which stays above is y is equals to x cube between 1 to infinity. Now, as we all can notice very clearly that from minus infinity to plus infinity, the graph doesn't break, which means it is continuous. And if it is continuous, the points of discontinuity will be 0. So if they are asking you non-continuity based points, then I'll say the value of n will be 0. Do you all agree with this? But again, when somebody asks a question related to differentiability, I'll say look at the sharp turns. And if I were to make any comment on the sharp turns, this is your first sharp turn, this is the second sharp turn, I hope you can notice it, this is the third sharp turn. Are you noticing these three sharp turns, minus 1, 0 and 1? So at these 3 points, the curve is showing sharp turns, which means it, despite being continuous, will be a non-differentiable functions. And that is why I'll say the number of non-differentiability of this curve, the number of points of non-differentiability of this curve will be 3. And if I'm asked m plus n, which is 3 plus 0, the answer will be 3. Did you understand the whole question, the entire solution? I hope it has given you a lot of clarity about differentiability as well. So majorly, we started with limits, then we moved to continuity, and then we talked about differentiability. You need to remember 3 things here very clearly: limit and the different methods of evaluating questions based on limits. Those concepts only are used in continuity because in continuity, we ensure that the value of the function at a point and the left hand limit and the right hand limit should be same so that the function can be called to be a continuous function, and some theorems related to continuity. And then we talked about differentiability. So the way we discussed continuity, the way we can talk about differentiability as well. But to check the differentiability, we need to check 2 things: the left hand derivative and the right hand derivative. I hope you remember it. If through limits, you can verify or validate that LHD and RHD are same through using the same concepts of limit, which we have started discussing in the beginning, you can verify whether a function is differentiable or not. But through graphs also, you can put some comments on the differentiability of the function, which we have already seen in this part. So I think you have brought a great clarity on this front, along with some theorems based on differentiability, which also we have discussed. So I think now we feel confident on this concept LCD. Remember, this is one of those simple chapters which does not have much to be discussed as far as the theory is considered. But you should remember these concepts because they are some simple chapters which can be learned with some standard decent efforts. And the gain is good. You will get some really good marks from this particular chapter. Limits, continuity, differentiability. Technically, they are 3 concepts, 3 chapters, but they are clubbed into 1 unit, LCD. And you can get a really good return from these units, these chapters. And I'm hoping that this chapter, this one shot has really helped you a lot. We'll definitely share the PDF, the handwritten notes as well, along with the DPPs for your practice in the real-time environment at absolutely no cost in our Elevate JEE crash course. This program is available on our PW app, the link to which is given in the description. You can click on it and access it at absolutely no cost. PW is an amazing platform from where millions of students are already preparing for different competitive exams at affordable prices. Without delay, do access it and avail all the features. And with that, let's call it a day. Thank you so much. Have a nice day.